This is how Smarties, Jolly Rancher, and Runts are made. From raw sugar and intense flavoring to high-speed mixers and molds, this process transforms simple ingredients into some of the most recognizable candies on the planet. Today, we go inside the factories to follow each step from cooking and shaping to coloring and packaging, revealing the precise machines and techniques that turn sugar into iconic candy. Smarties begin with sugar, which arrives in granulated form, stored in sealed stainless steel silos. Sugar is pneumatically transferred to the batching system through enclosed pipes. A fixed quantity of sugar is weighed and transferred to a rotating pan coder, which serves as the initial forming chamber. Inside the pan coder, fine misting nozzles spray a sugar solution to bind dry sugar particles. Centrifugal force distributes the syrup across the pan surface, while rotation builds uniform cores. These rotating pans are tilted slightly forward and spin at a constant rate to ensure layering occurs evenly on all particles. Each pass adds mass to the sugar cores, which slowly grow into uniform spheres. The syrup concentration is adjusted by flow meters to maintain proper adhesion without overcoating. Once the cores reach target size, they are dried using dehumidified air blown from a ring manifold mounted inside the pan. The dried sugar cores are sieved using vibratory screens to separate non-uniform particles. Undersized or misshaped cores are removed and recycled through a remelt system. Only cores within strict diameter tolerance proceed to the coating line. The selected cores are transferred by vacuum conveyor to the color coding pans. These pans are also tilted and use internal baffles to create tumbling action. Colored sugar syrup is sprayed onto the rotating cores using precision air-assisted atomizers. Each color batch is processed separately to avoid pigment contamination. The syrup contains food-grade dye and a fixed ratio of glucose to prevent crystallization. The color builds in thin, transparent layers with multiple passes. Air jets accelerate, drying between each pass without disturbing coating adhesion. A fixed weight of syrup is applied per kilogram of product to ensure consistent color intensity. Optical sensors monitor surface reflectivity to detect coating completeness. Each pan batch continues until desired hue and opacity are reached. After coloring, the coated Smarties move to a polishing stage where they are treated with a food-grade wax solution. This step is done in smaller polishing pans with a lower tilt angle and slower rotation. A fine mist of carnauba wax is sprayed using atomizing nozzles to create a thin surface layer. Polishing lasts 5 to 8 minutes, depending on batch size and wax viscosity. Final gloss level is checked using a reflectometer. Finished pieces are then cooled using ambient airflow and discharged onto an inspection conveyor. The conveyor passes beneath a digital camera array, which checks for shape consistency and surface defects. Air jets remove any pieces outside tolerance. The remaining product enters a vibrating chute that feeds into the printing station. Each Smartie is printed with a white edible ink letter using a rotary pad printer. The printer contains a silicone pad which presses into an ink-filled cliché plate to pick up the letter. The pad then presses onto the candy surface, which conforms slightly to ensure full transfer. Ink drying occurs almost instantly due to ethanol-based solvents. The printed pieces continue on a conveyor to a temporary holding bin. The bin meters product flow into the packaging line, which includes weighing scales and filling hoppers. Weighing scales use load cells to dispense exact net weight quantities into each chute. The chutes feed either roll wrapping machines or blister forming equipment depending on format. For roll packs, Smarties are released onto a continuous wrapper film. Film feeding is driven by a servo motor, which synchronizes with the candy drop. Once the set count is reached, rotary knives cut the film into individual lengths. Heat seal bars close both ends of the film around the product. Roll packs exit the machine and are stacked in cartons. Blister packs are made by forming cavities in thermoplastic film using vacuum and heat. Smarties are dropped into each cavity by a gate dispenser. A foil lid is laminated to the top of the film using a heated roller. Boxed formats involve volumetric fillers, which drop measured product into upright cartons. Cartons are formed from flat blanks using a rotary carton erector. Filled cartons pass through a hot glue sealing station before entering the coding unit. All packaged formats are printed with batch number and timestamp using thermal inkjet printers. Finished units move along conveyors to the collating area, where robotic arms group products into larger cases. Cases are formed by an automatic case erector, which folds and seals flaps using glue. Collated products are pushed into the case, and the top is sealed in a separate station. Each case is labeled using a print and apply system that adheres barcodes and contents description. Cases are transferred to palletizers, which stack them onto wooden or plastic pallets using a vacuum gripper arm. Stack height is determined by case weight and stability requirements. Full pallets are stretch wrapped with film before transfer to cold storage. Color production is kept isolated to prevent cross-contamination. Each color is made using dedicated syrup tanks and pump circuits. After each batch, the syrup lines are flushed with hot water, followed by a compressed air purge. Sugar syrup used for coating is heated in double-jacketed tanks with agitation. Temperature is maintained at 110 degrees Celsius for flow and binding properties. Syrup is filtered through a fine mesh screen before entering the coating pan spray system. Atomizing nozzles are adjusted for droplet size using air. Pressure regulators. Smaller droplets create smoother surfaces, while larger droplets increase build-up rate. The nozzle distance from product bed affects coverage radius and drying uniformity. Drying air is conditioned by passing through a desiccant dehumidifier and a preheater. Air temperature and humidity are set based on coating thickness. Flow rate is managed through adjustable louvers at the pan inlet. Pan rotation speed affects rolling frequency and layer adhesion. Faster speed increases agitation but can cause chipping. Slower speed allows better leveling of syrup layers but requires longer cycles. Optimal speed is determined for each pan size and batch load. Letter printing uses ink that contains titanium dioxide for opacity. The cliché plate is laser etched with letter shapes and mounted on a rotary drum. Each pad picks ink from the etched cavity and applies it to a passing candy unit on a timing belt. Positioning is maintained using optical encoders that sync the pad. Strike with the candy location. Missed prints are detected by contrast sensors. These pieces are removed using side air jets directed by the control unit. Packaging materials are fed from rolls mounted on unwind stations. Tension is controlled by dancer arms connected to motorized brakes. Registration marks on the film ensure cutting and sealing alignment. Heat seal jaws are PID controlled to maintain consistent seal strength. For rolls, twisted ends are formed using roller bars that compress the candy tube while rotating. The twisted sections are heat set to preserve shape. Cartons and boxes use cold form glue that is applied by nozzles onto folding flaps. Glue cure time is matched to conveyor speed and compression length. Cartons are held under pressure for 2 seconds to ensure bond strength. Filled cartons are buffered before case packing using a serpentine conveyor that absorbs flow variations. Cases are arranged in alternating layer patterns to improve stacking strength. Full pallets are weighed before wrapping to confirm case count. Throughout the Smarties production process, all mass transfer points are closed-loop systems to prevent material loss. Product handling uses gentle slopes and controlled angles to minimize breakage. Surfaces in contact with product are coated with anti-static and anti-stick layers. Production parameters are logged in real time, including syrup temperature, pan speed, air humidity, atomization pressure, print contrast, and packaging throughput. These values are compared to target set points every batch cycle. Waste product is collected at each rejection point and separated by type. Non-printed Smarties can be remelted and reused. Printed or overcoated pieces are ground and disposed of in a controlled waste stream. Jolly Rancher candies are produced by first preparing a concentrated sugar syrup, which serves as the structural base of the hard candy. Granulated sucrose is stored in silos and pneumatically transferred into batching hoppers positioned above stainless steel dissolution tanks. Liquid glucose or corn syrup is pumped from heated holding tanks and metered into the same batch tanks through insulated lines. The ratio of sucrose to glucose is fixed and varies slightly by flavor to affect hardness and glass transition behavior. Water is added last to the batch to begin dissolution. The tank uses an agitator with 3-blade impellers mounted on a vertical shaft that mixes all ingredients until fully homogenized. Tank temperature is held at 85 degrees Celsius to accelerate solubility without initiating premature boiling. Once dissolved, the sugar mixture is transferred to a continuous cooker via positive displacement pump. The cooker is a tubular heat exchanger that uses steam as a heating medium to bring the syrup to final cooking temperature. As the syrup flows through the tubes, internal temperature rises to approximately 160 degrees Celsius. This evaporates most of the water and converts the syrup into a thick, amorphous mass. The syrup exits the cooker under pressure and is fed directly into a vacuum chamber where remaining moisture is removed rapidly. Vacuum levels are controlled using a pressure regulator that lowers boiling point to minimize heat degradation. The product exiting the vacuum chamber has a moisture content of less than 2%. This highly viscous candy mass is discharged onto a stainless steel cooling table coated with a non-stick surface. A mechanical scraper arm moves the mass back and forth to reduce temperature and increase viscosity. Cooling continues until the mass reaches a pliable yet non-flowing state, typically at around 110 degrees Celsius. At this stage, acidulants such as malic acid or citric acid are added manually or through a heated dosing manifold. These acids provide the sharp fruit flavor profile typical of Jolly Ranchers. Simultaneously, concentrated flavor oils are added using a high shear mixer attached to the edge of the cooling table. Colorants are blended in at the same point and are selected to match each flavor. The flavoring and coloring step is brief because extended mixing can cause volatile loss. The candy mass is worked using mechanical paddles that fold and compress the batch until all additives are fully incorporated. This creates a uniform mass with consistent flavor distribution and visual appearance. The mass is divided into portions and transferred to a forming line using heated transfer arms. The forming line begins with a batch roller, which elongates the candy into a rope of constant diameter. The batch roller consists of 4 or 5 heated rollers that rotate in sequence and pull the candy through narrowing gaps. The temperature of each roller is individually controlled to prevent sticking. As the rope exits the final roller, it is passed through a rope sizer, which uses a die to shape the candy into an exact diameter. This diameter is based on the final desired piece weight and length. The rope is pulled forward by synchronized feed rollers, which deliver it into the die forming machine. The die forming machine consists of a rotating drum with recessed cavities. As the rope enters the drum, a knife presses it into the cavities and shears the candy at regular intervals. Each cavity is shaped like the final product and creates a pillowed form on the surface of each candy. Formed pieces are ejected from the die cavity using a release pin. Pieces fall onto a vibratory cooling conveyor that carries them away from the die head while further reducing internal temperature. The conveyor uses airflow and mechanical shaking to ensure the candies remain separated during cooling. Cooling continues until surface temperature falls below 40 degrees Celsius. At this point, the candy is sufficiently rigid to avoid deformation. Candies pass through an oiling drum, where a small amount of anti-stick oil is applied to prevent adhesion during storage. The candies are then conveyed to a storage bin or directly to the wrapping line depending on production sequencing. The wrapping machine used for Jolly Ranchers is typically a high-speed twist wrap unit. Formed candies are fed into a flighted conveyor that spaces them evenly before wrapping. Wrapping film is fed from a roll and cut into segments that match the length of each candy. A film grabber aligns each piece of film with the incoming candy. The machine wraps the film around the candy and twists both ends simultaneously using 2 rotating fingers. The twisted ends are pressed to retain their shape. Wrapped candies exit the machine on a discharge conveyor and are grouped automatically into rows for further handling. Each component of the line operates continuously and in coordination with upstream and downstream modules. Flavor changeovers require the flushing of flavor oil lines and cleaning of the color tanks. The cooling table surface is scraped and cleaned before introducing the next batch. Each flavor batch typically corresponds to a specific production run to avoid cross-flavor contamination. Color consistency is maintained by using pre-blended pigment dispersions added through precision pumps. These dispersions are stirred continuously in a heated jacketed tank before injection into the batch. Volume dispensed is controlled by a pulse counter that records each pump stroke. Flavor strength is managed by load cell feedback, which calculates the candy mass and adjusts flavor oil volume accordingly. The oils are kept in nitrogen blanketed tanks to reduce oxidation during storage. Rope speed through the batch roller is monitored by encoder feedback and automatically adjusts based on temperature, mass viscosity, and die pressure. A thermocouple embedded in the rope housing measures product temperature before it enters the die head. If the temperature is too low, the feed rollers reduce pull rate to prevent rope breakage. If too high, the batch roller slows to allow cooling. The forming drum speed is matched to rope speed using a gear ratio that ensures clean cuts at every cavity. Cavity pressure is balanced using pneumatic tensioners to avoid candy flash or deformation. As the knife cuts each candy, pressure sensors detect load and ensure alignment. Misformed candies are diverted by an air jet triggered by machine vision sensors that detect dimension or position errors. The vibratory cooling conveyor has a zone design with separately controlled fans. Airflow is filtered and directed through baffles that create a laminar stream. The shaker speed varies by batch size and surface stickiness to optimize separation. Oiling quantity is regulated by metering pumps connected to a fine mist nozzle array. Only a trace amount of oil is used to avoid impacting flavor or texture. Excess oil is collected in a catch tray and recycled through an inline filter. The twist wrapping film is made of cellophane or oriented polypropylene and pre-printed with branding and flavor identifiers. Film tension is controlled by a feedback loop that adjusts brake pressure on the film unwind shaft. Knife blades that cut the wrapping film are positioned by servo motors that adjust cut length in real time based on candy dimensions. Heat sealing is not used on these wraps because the twist retention is mechanical. The wrapping process operates at up to 1,000 pieces per minute and includes redundant feeders to reduce downtime. Candy positioning is controlled by optical sensors that detect each piece and signal the film release mechanism. Throughout the Jolly Rancher process, thermal conditions are tightly regulated to maintain texture and gloss. Humidity is controlled in the cooling and forming areas to prevent surface fogging or sugar bloom. Runts are produced by compressing flavored and colored dextrose-based powders into shaped tablets using rotary forming presses. The process begins with the blending of base ingredients in large capacity ribbon mixers. Dextrose, which forms the primary bulk of the candy, is loaded from silos through vacuum transfer lines into the mixer. To this, a precise amount of maltodextrin is added using screw-driven feeders. Citric acid powder is added to enhance flavor sharpness and to balance sweetness. Calcium stearate is introduced as a lubricant to prevent sticking during compression. Microcrystalline cellulose is used to improve structural integrity and reduce friability. Each component is weighed automatically by load cell-controlled bins before entry into the mixing chamber. Mixing occurs under low-speed agitation for uniform distribution of fine powders. After dry blending is complete, a liquid binding solution is sprayed into the mixture. This binder typically contains invert sugar or corn syrup diluted in water to enhance adhesion during compression. Spray nozzles mounted at the top of the mixer deliver atomized binder in controlled bursts while the mixer continues rotation. The partially moistened blend exits the mixer and is transferred via auger to a fluid bed dryer. The dryer uses filtered air heated to approximately 60 degrees Celsius to remove excess moisture while preserving binder functionality. The drying process takes between 15 and 20 minutes and ends when the target moisture content of around 1.5% is reached. Once dried, the mixture is cooled to ambient temperature through a vibrating cooling conveyor fitted with perforated air plates. The cooled material is then screened using a rotating sieve to break up clumps and ensure consistent particle size before compression. Oversized particles are ground and reintroduced into the feed stream. The prepared mix is transferred to an overhead hopper, which feeds directly into rotary tablet presses. Each press consists of a die table that rotates horizontally with multiple tooling stations. As the table turns, powder falls into open dies, which are then compressed between upper and lower punches. Each die cavity is shaped according to the desired fruit design, such as banana, grape, or strawberry. The punches apply high pressure for a brief duration, which compacts the powder into a solid mass. Ejection cams raise the lower punch to release the formed candy, which is then pushed out of the die onto a discharge belt. Compression force, dwell time, and punch speed are continuously monitored by sensors on each press station. Press speed is generally between 40 and 60 rotations per minute, depending on candy size and complexity. Multiple presses run in parallel to produce different shapes and colors. Formed candies exit the press at a controlled rate and are transferred by belt to the coating drums. These drums are inclined and rotate slowly to tumble the candy pieces without damaging them. A sugar syrup is applied via a spray manifold mounted inside the drum. The syrup contains dissolved sugar, colorants, and flavor oils specific to each fruit variant. Application of the coating syrup occurs in cycles with drying air blown between each layer. The syrup forms a smooth, glossy shell around the compressed candy core. The drying air is filtered and maintained at a temperature of 35 to 40 degrees Celsius to prevent syrup crystallization. Each coating drum batch completes between 12 and 15 cycles before final gloss is achieved. Color uniformity is monitored using inline optical sensors mounted at the drum exit. Any candy that fails color threshold is automatically diverted by air jets to a reject bin. Accepted candies continue to the polishing stage. Polishing drums are similar in design to coating drums, but operate at lower speeds. A light mist of food-grade carnauba wax is sprayed onto the tumbling candy to enhance surface shine. Polishing continues for 5 to 8 minutes until all pieces achieve uniform gloss. Polished candies exit the drum onto a vibratory conveyor, which aligns them for inspection. A camera-based sorting system checks each candy for cracks, deformities, or uncoated surfaces. Machine vision algorithms trigger solenoids to remove defective units from the flow. Correct candies pass to a final drying tunnel where low humidity air circulates to stabilize the coating. Tunnel dwell time is approximately 3 minutes. After drying, the candy enters the counting and filling station. The filling machine uses rotating discs with pockets that hold fixed numbers of candies. Each pocket empties into a vertical chute leading into packaging units. Depending on packaging format, the candy is dispensed into cardboard cartons, plastic tubes, or small bags. Film-fed vertical form-fill seal machines receive candy loads by timing screw and funnel. The machines form packaging film into tubes, seal the bottom, drop candy, and seal the top. Each package is cut and dropped onto a belt, leading to collection bins. Plastic tubes are filled by inline auger fillers that rotate open-bottom tubes beneath product chutes. A single rotation dispenses a set quantity of candy. Filled tubes are sealed with heat or snap-on caps, depending on design. Cardboard boxes are filled on a separate line using drop gate fillers. Boxes are preformed using a mechanical folder and pushed through filling lanes. After filling, a flap tucker folds and glues the top closed. All packaging units pass under an inkjet printer that applies batch codes and timestamps. Packages are then grouped using collating conveyors and shrink-wrapped or cased based on distribution requirements. Throughout production, each shape and flavor batch runs in dedicated equipment zones to prevent cross-contamination. Banana-shaped candies are yellow and flavored with isoamyl acetate. Strawberry-shaped candies are red and flavored with ethyl methylphenylglycidate. Grape, lime, and orange follow similar combinations of shape, color, and ester-based flavoring. Each flavor's syrup is prepared in separate jacketed tanks to preserve aromatic quality. Syrup concentration is adjusted to match coating viscosity for that flavor's specific sugar crystal structure. Color pigments are pre-blended in glycerin or propylene glycol and introduced during syrup preparation. The compressed candy core has a fixed porosity that allows coating to adhere without absorption. Compression tooling is polished and coated with anti-stick materials to maintain shape definition and reduce mechanical drag. Die cleaning is performed at regular intervals using brush systems that rotate within the die cavity. Punch alignment is verified using a laser sensor that checks deviation in vertical axis during operation. Air supply for fluid bed drying, cooling, and coating is sourced from a centralized HVAC unit with HEPA filtration. Ducting routes temperature and humidity-controlled air to each stage through pressure-controlled dampers. All rotary presses, coating drums, and polishing machines are synchronized via a central PLC that tracks product flow and batch progression. Any variance in throughput or processing time automatically adjusts downstream processes to maintain balanced output. Candy weight is checked at the end of the forming line using a dynamic scale belt. If a candy is too light or too heavy, it is removed before coating. Moisture content of coating is measured using infrared sensors to determine residual water before drying. Compression tooling for runts is machined from hardened stainless steel and engraved with shape detail using CNC lathes. Replacement tooling is stored in temperature-controlled drawers to prevent thermal distortion. Punch lubrication is automated with small volume silicone oil injections at each cycle. Candy density is maintained at a specific range to avoid breakage during packaging. Too much compression leads to brittle texture, while too little causes shape distortion. Process control data is logged continuously and reviewed for each shift. At no point is the candy handled manually until fully wrapped or boxed. The entire line from blending to packing operates as a continuous feed with variable speed, drives that adapt to real-time conditions. The manufacturing process of Kinder Bueno begins with the preparation of the wafer batter. The primary ingredients, wheat flour, water, vegetable oil, lecithin, and leavening agents, are fed from storage silos and tanks into a stainless steel batching system. Each component is dosed with gravimetric precision, and the batch is mixed in a jacketed high-shear mixer. The flour is delivered via screw conveyors, water is flow metered, and emulsifiers are introduced through liquid dosing pumps. Mixing time, rotation speed, and temperature are regulated to ensure that the batter reaches a uniform consistency suitable for rotary plate baking. Viscosity is continuously measured during mixing to maintain the desired flow behavior. The mixed batter is transferred to the baking system via diaphragm pumps. A rotary oven equipped with a sequence of upper and lower metal baking plates receives the batter through a synchronized volumetric depositor. The baking plates close, forming a mold that defines the half-shell structure of the wafer casing. The plates travel through the baking chamber where they are heated via direct flame or electric elements. Internal plate temperature is maintained between 160 degrees Celsius and 180 degrees Celsius, with each shell requiring approximately 90 seconds of exposure to solidify and develop structural integrity. As the mold progresses through the oven, moisture is evaporated, and a thin, crisp wafer forms along the contours of the mold cavity. Upon completion of the baking cycle, the plates open automatically. Mechanical lifters remove the wafer shells and place them onto a wire mesh conveyor. The shells are cooled using forced ambient air delivered through adjustable nozzles positioned above and below the conveyor. The shells then enter a trimming station where a high-speed rotating blade removes excess material from the shell edges to ensure uniform shape and dimension. The trimmed shells are rotated and aligned into uniform orientation using guide rails and belt positioners. The output is arranged into index stacks for timed transfer to the filling system. The hazelnut cream filling is produced on a separate line. Whole hazelnuts are delivered in bulk and transferred into a vibratory screening unit that removes any residual shell fragments or extraneous material. The screened nuts are routed through a mechanical conveyor to a continuous roasting system. Roasting is carried out in a rotating drum oven or a belt-type hot air roaster. The roasting temperature is controlled at 150 degrees Celsius to 160 degrees Celsius, with exposure times ranging from 20 to 25 minutes depending on kernel size. Roasted hazelnuts are cooled rapidly using counterflow ambient air to prevent oil migration. Blanching follows, using mechanical abrasion rollers to remove the skin. Blanched nuts are transported directly to the grinding section. Hazelnut grinding is conducted in 2 stages. The first stage uses a hammer mill or pin mill to reduce particle size to below 200 microns. The ground nut mass is then passed through a ball mill where particle size is further reduced to below 30 microns. The resulting hazelnut paste is transferred to a mixing tank equipped with counter-rotating blades. To this paste, specific quantities of refined sugar, vegetable fat, milk powder, and lecithin are added. The blend is agitated at a controlled temperature, generally between 35 degrees Celsius and 40 degrees Celsius, to produce a homogeneous, spreadable cream. Once fully emulsified, the hazelnut cream is transferred to buffer tanks maintained at a consistent temperature and mixed gently with slow-speed impellers to preserve structure. Wafer shells are filled using a precision depositor that aligns with each open wafer cavity. The hazelnut cream is pumped through heated stainless steel lines and dispensed in measured volumes through multiple nozzles. The depositor operates in cycles synchronized with the conveyor to allow for accurate deposit into each cavity. Each half shell receives a center-aligned column of cream filling, stopping short of the rim to accommodate sealing with the upper half shell. After deposition, the second wafer half is picked and placed onto the filled shell using robotic vacuum grippers. Sealing of the wafer is carried out with a dual pressure belt system that presses both halves together at controlled force. The sealed wafer unit is transferred to the next processing stage, where the internal coating is applied. A tempered chocolate mixture is circulated through a closed-loop system and delivered to the coating station. Each sealed bar passes beneath a chocolate curtain that applies a uniform internal chocolate layer around the wafer structure. An excess removal mechanism uses vibration and compressed air knives to prevent pooling or uneven distribution. The coated units then enter a cooling tunnel, which uses recirculated chilled air to bring the chocolate to a solid state without thermal shock. Tunnel dwell time is determined by belt speed and tunnel length, ensuring full crystallization of the chocolate layer. After internal cooling, bars are conveyed to the external enrobing line. This section applies the milk chocolate outer coating. The coating chocolate is prepared in advance by melting, tempering, and circulating through jacketed pipes maintained at 30 degrees Celsius to 32 degrees Celsius. The bars pass over a mesh belt conveyor under an overflow system, where chocolate is applied to the top, sides, and bottom simultaneously. The base layer is achieved through contact with a rotating chocolate-coated roller positioned beneath the belt. Excess chocolate is removed using oscillating air jets and a vibrating belt section. Once the milk chocolate layer is set, decorative stripes of dark chocolate are applied. A multi-head depositor positioned above the belt releases thin lines of dark chocolate in a controlled motion pattern, creating the characteristic curved stripe design. The application of stripes is synchronized with belt movement, and chocolate flow rate is controlled using peristaltic pumps and pressure regulators. The decorated bars are sent through a secondary cooling tunnel. This unit is divided into multiple temperature zones, gradually reducing the product temperature to ensure final structure without bloom or surface defects. After exiting the second cooling tunnel, the finished bars are individually wrapped using horizontal flow wrapping machines. Each bar is conveyed into a forming box where the wrapper film is folded around the product and sealed longitudinally by heated rollers. End seals are created using rotating sealing jaws that compress and heat seal the film ends. The temperature, jaw pressure, and dwell time are adjustable parameters based on film type and bar temperature. The wrapping material is pre-printed with branding and is fed from reels under tension-controlled rollers. Wrapped bars are grouped by rotary collectors and transferred to the bar collation unit. This unit counts bars and arranges them for packaging into twin packs or other desired formats. Grouped units are transferred into pre-formed secondary sleeves or cartons. These are closed with mechanical tucks or glue application systems, depending on the product configuration. The fully assembled and sealed cartons are discharged from the line at regular intervals. At no point during the process are the components exposed to cross-contamination, as each line is physically separated and supplied with dedicated material flow and thermal systems. The entire production line is configured to operate in continuous motion, with conveyors, deposition units, coating systems, and cooling tunnels fully synchronized. All components, from batter mixing to final wrapping, are connected through an uninterrupted mechanical chain, resulting in fully assembled, filled, coated, and wrapped Kinder Bueno units. Production of Bounty begins with the formation of the coconut filling. The core ingredient, desiccated coconut, arrives in bulk and is stored in sealed silos or stainless steel containers. The coconut is unloaded via vacuum conveyors into pre-cleaning units, where it passes through a series of vibratory sieves and magnetic separators to remove oversized flakes, fine powder, and metal fragments. After initial screening, it enters holding hoppers equipped with agitation paddles to prevent bridging during downstream feeding. From the hoppers, desiccated coconut is metered into large-scale batch mixers. In parallel, a blend of glucose syrup, invert sugar, and emulsified fats is prepared. Glucose syrup is stored in heated bulk tanks and is circulated through jacketed piping systems to maintain flow at a consistent temperature between 45 degrees Celsius and 60 degrees Celsius. The syrup is pumped into dosing vessels, where flow rate is precisely controlled via mass flow meters. Invert sugar, used for moisture retention, is added next. Solid fats, typically palm kernel or coconut oil, are stored in insulated tanks, liquefied by indirect heating, and pumped through a closed-loop recirculation system to maintain fluid consistency. The syrup-fat mixture is introduced into the batch mixer with the desiccated coconut. The mixer, usually a double Z paddle or ribbon blender, operates at low to medium shear to avoid breaking the coconut structure while ensuring even distribution of binders. The mixing chamber is jacketed to maintain the blend at 40 degrees Celsius to 45 degrees Celsius, aiding uniform fat dispersion. Mixing duration is controlled by programmable logic controllers and typically runs for 8-12 minutes per batch, depending on volume. Load cells beneath the mixer verify batch mass consistency. The completed coconut mixture is discharged through a pneumatically controlled gate valve onto a spreading conveyor. This conveyor leads to a slab, former consisting of a series of compaction rollers and edge formers. The mixture is shaped into a continuous ribbon or slab of fixed width and height. A top leveling blade smooths the surface, and lateral guides maintain slab width, typically between 100 mm and 150 mm. Roller pressure and conveyor speed are adjusted to control slab density and moisture distribution. The continuous slab moves into a cooling tunnel to solidify the matrix prior to cutting. The tunnel uses chilled air circulated by variable speed blowers. Tunnel length ranges from 15 to 25 meters, depending on line throughput, and internal temperature is maintained between 5 degrees Celsius and 10 degrees Celsius. Dwell time in the tunnel is approximately 3-5 minutes, enough to reduce the slab surface temperature to below 15 degrees Celsius. Exiting the cooling tunnel, the solidified slab is conveyed towards the portioning system. It first encounters a longitudinal cutting unit consisting of rotary disc blades that slice the slab into multiple parallel lanes. Blade spacing is adjustable based on final product width. These lanes proceed to the transverse cutting station equipped with servo-controlled guillotine knives. Blade actuation is synchronized with conveyor speed to ensure precise cut length, generally between 55 mm and 65 mm per piece. Each resulting rectangular coconut core is now a preform ready for enrobing. These preforms are transferred via a servo-driven indexing conveyor onto a perforated steel mesh belt leading into the enrobing section. In the enrober, the preforms pass beneath a tempered milk chocolate curtain. The chocolate, maintained at 30 degrees Celsius to 32 degrees Celsius, is pumped from a holding tank that continuously circulates it through a tempering unit. The tempering process cycles the chocolate through heating, cooling, and reheating, producing a stable beta crystal structure for gloss and snap. As the coconut bars pass beneath the chocolate curtain, they receive full top and side coverage. Simultaneously, a bottoming roller applies chocolate to the base through contact with the lower mesh belt, which has been pre-coated with a thin chocolate layer. Total chocolate deposition is regulated by overflow weirs and return flow pumps. After enrobing, the bars enter a vibrating section, which removes excess chocolate and promotes even distribution across the surface. Next, the enrobed bars pass under dual air knife systems, which blow away excess chocolate and refine the final bar shape. The air knives are positioned above and to the sides of the conveyor belt and deliver high-velocity air streams shaped by nozzles. Air pressure and flow direction are adjustable to control surface smoothing and eliminate drips or streaks. From here, the bars enter the cooling tunnel for chocolate crystallization. This tunnel is temperature zoned, typically starting at 12 degrees Celsius and gradually reducing to 6 degrees Celsius. Multiple air curtains prevent moisture intrusion. The cooling belt is constructed from food-grade plastic or stainless mesh and runs at a speed coordinated with enrobing throughput. Time inside the tunnel varies between 8 and 12 minutes, depending on bar dimensions and chocolate mass. Upon exiting the tunnel, the cooled bars are transferred via synchronized belts to the wrapping line. The wrapper feed system pulls pre-printed film rolls into a forming collar, where the film is shaped into a tube around each bar. The longitudinal seal is created by a heated roller or ultrasonic sealer. Transverse seals are applied at both ends by heated rotary jaws. The wrapping material is a multi-layer laminate typically composed of oriented polypropylene and metallized films for moisture barrier performance. The wrapping machine cuts and seals at rates exceeding 300 units per minute. Temperature, tension, and registration are electronically controlled. Eye marks on the film align the print with the bar position. Any deviation beyond +1 mm triggers automatic correction. Wrapped units are discharged via conveyor to a belt that aligns them for secondary collation. Depending on format, bars are grouped into twin packs or multi-packs. Mechanical pushers or robotic pickers load grouped units into cartons or wraparound sleeves. These cartons are formed from flat blanks fed from a magazine and folded using pneumatic actuators. Glue is applied at specific points by hot melt applicators, operating between 160 degrees Celsius and 180 degrees Celsius. Carton forming and glue compression are synchronized with product loading to ensure square, tight packages. Each carton is then indexed onto a conveyor for further grouping if needed. Although palletizing is excluded from this explanation, the output at this point consists of individual or grouped bounty bars, fully formed, enrobed, cooled, wrapped, and mechanically packed in a continuous flow operation. The production process is continuous, with coconut mass production, slab forming, cutting, chocolate tempering, enrobing, cooling, and packaging all connected via coordinated mechanical systems. Component flow is fully synchronized. All pumps, motors, conveyor drives, cutting blades, and enrobing units are driven by variable frequency drives and controlled via programmable logic controllers. Sensor arrays track mass, temperature, flow rate, belt speed, and chocolate level at multiple points. Each mechanical action is executed with predefined parameters for precise size, mass, and texture control. At no point is there any batch handling beyond the initial coconut sugar fat mixing phase. Once the slab is formed, the process is entirely linear and uninterrupted. Chocolate is continuously tempered and recirculated. Belt tension and alignment are automatically corrected by sensors positioned at key transition zones. All rotating equipment is balanced to minimize vibration and mechanical wear during high-speed operation. The only thermal processes are the initial cooling of the coconut mass to retain structural integrity during cutting and the two-stage cooling of the enrobed bar for chocolate crystallization. These are separated and isolated to prevent temperature overlap and ensure phase separation between fat-based ingredients and sugar syrups. Production of Baby Ruth chocolate bars begins with preparation of three major internal components: nougat base, caramel layer, and roasted peanuts. Each is manufactured separately in dedicated lines before being combined, enrobed, cooled, and wrapped. Nougat preparation begins by heating a sugar syrup composed of granulated sugar, corn syrup, and water in stainless steel cooking kettles. The mixture is continuously agitated with paddle mixers while being brought to a target temperature between 115 degrees Celsius and 125 degrees Celsius. The heated syrup is transferred via jacketed piping to a whipping kettle. In parallel, a protein solution, commonly egg white solids or milk protein concentrate rehydrated with water, is prepared in a separate mixing vessel and whipped at high speed using rotary whisks to introduce air and build foam structure. The hot syrup is gradually introduced into the aerated protein foam under continuous mixing. The injection is controlled with a metering pump to regulate flow rate and avoid protein collapse. Once combined, The mixture forms a dense but aerated nougat base. Additional flavoring agents, such as vanilla or milk powder, are introduced at this point. The nougat is discharged onto a cooling table or directly onto a continuously moving belt coated with release agent. The mass is shaped into a sheet using roller levelers that compress it to a uniform height, generally between 12 mm and 18 mm. Edge guides ensure consistent width. The nougat sheet passes through a cooling tunnel with forced air at 5 degrees Celsius to 10 degrees Celsius, solidifying the mass to prepare for the caramel layer. Dwell time in the tunnel is determined by line speed and product thickness. The cooled nougat sheet exits the tunnel and proceeds to the caramel application station. Caramel is prepared in a continuous cooker using a blend of glucose syrup, sweetened condensed milk, sugar, and butterfat. The ingredients are heated in a scraped surface heat exchanger where temperature is raised to 115 degrees Celsius, 120 degrees Celsius, allowing moisture reduction and Maillard reaction for color and flavor development. The cooked caramel exits through a static mixer and flows into a deposit manifold. Caramel is applied in a controlled layer onto the surface of the moving nougat sheet. A spreader bar or leveling roller ensures even thickness, typically between 5 mm and 8 mm. The sheet, now composed of nougat and caramel, passes through a secondary cooling tunnel to lower the temperature of the caramel to a semi-firm consistency. Cooling prevents deformation and facilitates cutting. At the peanut feeding station, roasted peanuts are applied onto the tacky caramel layer. Peanuts, previously roasted at 150 degrees Celsius, 170 degrees Celsius for 20-25 minutes, and cooled, are distributed from a hopper via a vibratory feeder. They are released through multiple chutes spaced laterally to ensure even coverage. A compression roller lightly presses the peanuts into the caramel, anchoring them mechanically. Excess or misaligned peanuts are removed by a combination of rotating brushes and air jets. The layered slab, now consisting of nougat, caramel, and embedded peanuts, proceeds to the portioning station. First, longitudinal cutting blades divide the sheet into multiple lanes, matching the width of the final bars. Rotary disc blades mounted on servo arms maintain cutting precision at high speeds. Next, transverse cutting is performed with guillotine knives that are synchronized with belt speed to produce exact bar lengths. Standard bar length ranges between 80 mm and 100 mm, depending on pack size. Each individual bar is spaced out on a conveyor and conveyed to the enrobing line. Enrobing is performed using milk chocolate prepared in tempering units. Solid chocolate blocks are melted in jacketed tanks at 45 degrees Celsius, 50 degrees Celsius. Melted chocolate is tempered using a 3-stage heat exchanger that brings the temperature down to 28 degrees Celsius, 30 degrees Celsius, before raising it slightly to 31 degrees Celsius, 32 degrees Celsius, optimizing crystal structure. Tempered chocolate is pumped to the enrober and flows over a curtain that uniformly coats the top and sides of each bar. The underside is coated by the bar contacting a chocolate film spread onto the mesh belt. The enrober uses a closed-loop recirculation system with a filter to remove solid debris such as peanut fragments. Chocolate viscosity is continuously monitored and adjusted by recalibrating the temperature or adding cocoa butter as needed. As the enrobed bars exit the curtain, they pass over a vibrating section that removes excess chocolate and evens out the coating. Air knives located above the belt blow off remaining drips and define the shape of the chocolate coating. Decorative top striations are formed by additional nozzles or vibrating wires that create surface patterning before the chocolate solidifies. Coated bars enter a cooling tunnel that is divided into multiple thermal zones. Temperature decreases gradually from 12 degrees Celsius to 5 degrees Celsius along the tunnel length. Air is dehumidified to prevent condensation and maintain surface gloss. Conveyor belt speed is regulated to maintain a dwell time of 10-14 minutes, allowing full crystal formation within the chocolate and ensuring coating integrity. After cooling, bars exit the tunnel and proceed directly to the wrapping system. Horizontal form-fill-seal machines handle individual wrapping. Printed film is fed from a roll and shaped around the bar using a forming collar. Longitudinal seals are made with heated rollers, and transverse seals are applied with rotating jaws. Seal parameters are set according to film type, typically biaxially oriented polypropylene. Eye-mark sensors on the wrapper film ensure print alignment with bar positioning. Wrapped bars are discharged from the flow wrapper and directed onto collection belts. Depending on final packaging format, bars are grouped into singles, multi-packs, or inserted into cartons. Collation is handled by diverters and indexing conveyors that control product spacing and group counts. Cartoning is performed using automatic cartoner machines that erect, fill, and close cartons in one continuous motion. Hot melt glue is dispensed by nozzle applicators to seal carton flaps. Carton size and closure mechanism are adjusted based on product format. At this stage, the complete Baby Ruth bars have undergone mechanical and thermal transformation from raw syrup, milk solids, and nut ingredients into structured, layered, enrobed, and wrapped units. From initial syrup cooking to final wrapping, all steps are continuous and synchronized by servo-driven machinery, sensor-guided conveyors, and recipe-controlled dosing systems. No manual handling is present between slab formation and wrapping. All ingredient transitions are facilitated through pumps, screw feeders, and belt conveyors. Mixing, cooking, spreading, cooling, cutting, coating, and wrapping occur in physically distinct but functionally integrated process zones. The nougat structure is controlled by syrup concentration, aeration speed, and protein matrix strength. Caramel consistency is determined by temperature profile and solids content. Peanut adhesion is achieved by compression into a semi-set caramel phase. Chocolate crystallization is stabilized by controlled tempering and gradual cooling. Final bar geometry is maintained by precision portioning and belt tracking. Line speeds are configured to produce hundreds of bars per minute, with each step calibrated for thermal load, product viscosity, mass consistency, and dimensional tolerance. The entire operation functions as a continuous flow line, driven by precise thermal, mechanical, and depositional parameters. The result is a consistently shaped, layered, and enrobed chocolate bar manufactured through a sequence of interdependent, high-speed industrial systems. Producing 10 million Snickers bars begins with raw ingredients delivered in industrial-scale volumes. Liquid glucose, granulated sugar, skimmed milk powder, cocoa liquor, cocoa butter, vegetable fats, peanuts, egg white, lactose, and emulsifiers. All materials are stored in temperature-controlled silos, tanks, or hoppers, connected by stainless steel pipelines and pneumatic conveyors to feed the production lines with uninterrupted flow. The first step is the nougat base. A pre-blend of sugar, glucose syrup, and water is piped into a continuous cooker. This cooker operates under controlled heat and vacuum, rapidly boiling the mixture to reach the target solid's content while minimizing color and flavor degradation. The hot syrup exits at around 120 degrees Celsius and is sent straight into a high-speed whipping chamber. Inside the whipper, dried egg white and milk powders are injected. A rotor-stator system beats the mix at high speed, incorporating air into the matrix to create the nougat's aerated structure. The density is tightly regulated with inline sensors measuring viscosity and expansion ratio in real time. Once aerated, the warm nougat mass flows through heated stainless steel pipes and is deposited as a continuous sheet onto a wide belt coated with a release film. As the sheet advances, calibrated rollers compress it to a uniform height, typically between 12 and 15 millimeters. The sheet then passes through a cooling tunnel that drops its internal temperature below 20 degrees, stabilizing the structure for the next layer. Once cooled, the caramel layer is applied. Caramel production occurs in a separate closed-loop cooker, where a mixture of glucose syrup, sugar, dairy fats, and milk solids is cooked under vacuum to reach the desired viscosity and chew. The caramel exits the cooker at around 118 degrees and flows into a depositing manifold. This manifold lays a smooth, uniform layer of hot caramel directly onto the nougat sheet. While the caramel remains soft, whole roasted peanuts are added. Peanuts, sourced in bulk, are first passed through an inline sifter to remove debris, then lightly roasted in continuous rotary ovens. After roasting, they are cooled and metered onto the caramel layer using a vibratory conveyor with adjustable baffles. The conveyor distributes peanuts evenly across the moving sheet, ensuring every section contains a balanced nut density. The peanut caramel nougat tri-layer now proceeds through a final compression roller, bringing it to the finished bar thickness. From here, the slab enters a chilling tunnel that gradually reduces its temperature from ambient to below 10 degrees C over a span of 20 meters. This ensures the caramel sets just enough to be cleanly cut without oozing or deformation. After chilling, the slab moves to a guillotine cutter. First, rotary blades cut it lengthwise into continuous ribbons, each the width of a Snickers bar. Then, a high-speed guillotine slices each ribbon into uniform bar-sized segments using servo-controlled motion synchronized with the belt speed. Blades are coated with a non-stick surface and cleaned automatically to prevent buildup. Each freshly cut bar now enters the enrobing stage. Bars are transferred onto a wire mesh conveyor belt and passed beneath a curtain of tempered milk chocolate. This chocolate is continuously circulated through a 3-stage tempering system, where it is heated, cooled, and reheated to create stable cocoa butter crystals. The chocolate is maintained at 30 to 37 degrees Celsius, ensuring proper viscosity and flow. As each bar passes through the enrober, it is coated on all sides, top, bottom, and flanks. The base of the bar receives a bottoming layer of chocolate from a pre-flooded section of the belt. Excess chocolate is removed by an adjustable air knife that blows a focused jet across the bar's surface, shaping the characteristic swirl patterns on top. A vibrating section under the mesh belt removes bubbles and smooths the surface. The enrobed bars enter a cooling tunnel that spans 30 meters and consists of multiple zones. Each zone gradually reduces the air temperature, allowing the chocolate to crystallize evenly. The final zone chills the bars to below 8 degrees Celsius, locking the coating into a firm, glossy finish with the correct snap and bloom resistance. After exiting the tunnel, each bar is inspected by a vision system. High-resolution cameras scan every unit for shape, surface quality, alignment, and chocolate coverage. Defective bars, those with missing peanuts, air gaps, or surface defects, are automatically rejected through pneumatic diverters. Accepted bars move on to the wrapping section. Each bar is fed into a flow wrapping machine running at speeds of up to 100-200 bars per minute. Wrapping film, pre-printed with branding and batch codes, is drawn from a roll and cut to size by rotary knives. As each bar passes through, it is wrapped in film, heat sealed along the underside, and crimp sealed at both ends. The sealing jaws operate with synchronized thermal and pressure settings to create tight, tamper-proof packages. Wrapped bars are conveyed through a metal detector calibrated to detect both ferrous and non-ferrous contaminants. Any bar triggering the system is rejected. Compliant bars continue to the check weigher, which confirms unit weight to within plus and 1.5 grams. Any deviation results in immediate removal from the line. The verified bars are then grouped and collated. Robotic arms pick up sets of bars, typically 24, 36, or 48, and place them into cartons automatically erected from flat, blanks, Hot melt glue is applied by precision nozzles to secure the flaps. Cartons are closed, sealed, and printed with best before dates using high-speed inkjet coders. Cartons then advance to the palletizing station. Here, robotic palletizers arrange the cartons into stacks on standard Euro or GMA pallets, using a pre-programmed pattern that alternates layer direction for stability. Slip sheets are inserted automatically between layers. Once a pallet is complete, it is wrapped with stretch film by a rotating arm that applies the film under tension to create a rigid, transport-stable unit. Throughout the entire process, programmable logic controllers coordinate equipment motion, timing, and feedback across the line. Each machine is connected to a centralized SCADA system that logs production metrics, sensor values, fault codes, and output counts in real time. Operators monitor touchscreen panels displaying temperature trends, motor speeds, belt loads, fill levels, and inspection alerts. The chocolate tempering unit is governed by 3 separate thermal zones, each independently controlled by thermocouples and heating elements. Syrup bricks is measured inline using optical refractometers. Nougat density is monitored by in-pipe density meters. Caramel viscosity is controlled by adjusting vacuum level and cook temperature. Every variable is closed-loop controlled, meaning it adjusts itself based on sensor readings. Carbon dioxide is used in modified atmosphere packaging for bulk storage formats. The gas is injected into large multi-bar containers to displace oxygen, extending shelf life. These containers are flushed, sealed, and stored in chilled holding bays before being distributed. Clean-in-place systems automate sanitation. Heated caustic detergent flows through all nougat, caramel, and chocolate handling systems at the end of each run. Pipes, tanks, depositors, and pumps are cleaned in sequence, followed by hot water and sanitizing rinse. Each cycle is logged with flow rate, contact time, and temperature. To produce 10 million Snickers bars, the line operates continuously for multiple days across several parallel lines. A single high-speed line can produce up to 1,100 bars per minute. With 10 such lines running in tandem, nearly 720,000 bars are produced per hour. In under 14 hours, 10 million bars are complete. Each bar is mechanically identical. Same mass, same shape, same structure. From aerated nougat to sticky caramel, crunchy peanuts, and smooth milk chocolate coating, the process controls every variable. Flow meters, torque sensors, load cells, vision cameras, pH probes, temperature controls, and synchronized motors maintain the consistency required for mass production. Every action is automated, but none is simple. The caramel must flow, but not run. The nougat must hold its structure without hardening. Peanuts must fall in even distribution without clumping or rolling. Chocolate must be tempered, coated, shaped, and solidified, without bloom, swirl misalignment, or trapped air. Producing 10 million Reese's peanut butter cups begins with the bulk delivery of core ingredients: roasted peanuts, cocoa liquor, cocoa butter, sugar, salt, milk solids, dextrose, emulsifiers, and stabilizers. Raw materials arrive in tankers, super sacks, and silo containers, and are fed into the production system via automated pneumatic transfers, conveyor augers, or liquid pumps, all connected to centralized control systems that regulate flow, temperature, and mass. The peanut butter core is produced first. Whole roasted peanuts are delivered directly into an industrial-size vibrating hopper. The hopper separates debris, splits, and undersized fragments through a combination of screen grating and air jets. The selected peanuts are passed through a second roasting stage in a continuous rotary drum oven, bringing their internal temperature above 160 degrees C. This ensures uniform oil release and deepens flavor. As they exit the roaster, the peanuts are immediately cooled using a forced air cyclone system to prevent over-roasting. Cooled peanuts are fed into a hammer mill, where rotating steel blades grind them into a fine, warm paste. The paste flows directly into a ribbon blender, where sugar, salt, dextrose, and stabilizers are added. The blender's high shear paddles fold and mix the ingredients, creating a thick, creamy filling with a controlled moisture content and spreadable viscosity. Viscosity sensors and torque meters monitor the blend in real time. The finished peanut butter is pumped into heated jacketed holding tanks equipped with agitators that keep the filling homogeneous and at a stable flow temperature around 45 degrees Celsius. Meanwhile, chocolate production runs in parallel. Cocoa liquor, cocoa butter, sugar, milk solids, and lecithin are fed into a high-capacity conche. The conche kneads and heats the mixture, allowing moisture and acidity to evaporate. Internal temperature is held between 50 °C and 60 °C. Once the flavor has developed and the texture has been refined to a smooth mass, the mixture is transferred to a 5-roll refiner. In the refiner, steel rollers shear the chocolate mass to reduce particle size to below 20 microns. The refined chocolate is then conched again to polish the particle surfaces, improve flow, and enhance melt. From the conche, the liquid chocolate is pumped through heat-maintained stainless lines into tempering units. Tempering machines cycle the chocolate through 3 thermal zones: heating to fully melt all crystals, cooling to encourage stable seed crystal formation, and reheating to melt unstable forms. The result is chocolate with stable beta crystals that produce a glossy finish and crisp snap. Now the forming line is activated. Pre-formed paper cups are dispensed from a magazine feed into indexed molds on a conveyor belt. A depositor head descends over each cup and fills the base with a measured dose of tempered chocolate. This forms the bottom, shell. As the chocolate hits the cup, the molds are vibrated rapidly, forcing the liquid to spread evenly and coat the cup base. The conveyor then carries the partially filled cups through a cooling tunnel that drops the chocolate temperature to around 10 degrees Celsius over several minutes, solidifying the shell and contracting it slightly away from the paper wall. Next, the peanut butter filling is applied. A piston depositor, aligned with the mold indexing system, dispenses a precise slug of peanut butter directly onto the cooled chocolate base. The volume is tightly controlled, typically 10 to 15 grams per cup, depending on size variant. The warm filling spreads slightly on contact, but retains its form due to its balanced fat structure and cooling effect from the base. A brief second cooling tunnel pass stabilizes the core enough to support the top chocolate layer. The top layer of chocolate is deposited last. Another depositor head applies a final pour of tempered chocolate over the peanut butter core. Vibration removes any trapped air and flattens the surface to an even plane. This final deposit seals the core entirely, forming the completed cup. The filled cups now pass through the primary cooling tunnel, a multi-zone chamber that gradually drops the internal temperature of each cup to ensure uniform crystallization. Airflow, humidity, and conveyor speed are precisely tuned. The full cooling cycle lasts around 10 minutes, allowing the chocolate to fully solidify without forming sugar bloom or fat migration marks. As the cups exit the tunnel, they undergo automated inspection. Vision systems scan every unit for fill height, surface uniformity, and alignment within the paper cup. Cups with off-center deposits, cracked surfaces, or exposed peanut butter are automatically rejected by robotic arms or pneumatic gates. Approved cups continue to the wrapping station. A pick-and-place system lifts each cup and transfers it to the wrapping in-feed. Wrapping film, pre-printed with branding and registration marks, is cut to size and wrapped tightly around each cup using a twist wrapping mechanism. The ends are pinched and twisted shut by synchronized spinning belts. Wrapping speeds can exceed 1,000 units per minute per line. Wrapped cups are conveyed through a metal detector calibrated for high sensitivity to both ferrous and non-ferrous contaminants. Any package triggering an alert is automatically diverted. Cleared products are grouped into collating lanes. Collators arrange cups into blister trays or multi-packs. A robotic grouping arm aligns sets of cups and loads them into thermoform trays or folding cartons. These cartons are pre-formed in a high-speed erector. Hot melt adhesive is applied to flaps, and cartons are sealed using servo-driven compression plates. Cartons are printed with date codes and batch numbers using thermal inkjet or laser coders. Completed cartons move toward the palletizing area. Robotic palletizers lift cartons using vacuum, grippers or adjustable forks, and stack them onto wooden or plastic pallets in a fixed interlocking pattern. Slip sheets may be added between layers. Each full pallet is conveyed to a stretch wrapper. A rotating arm applies film from bottom to top, binding the load securely for transportation. All stages are governed by programmable logic controllers. Each machine communicates via industrial Ethernet to a centralized control room. SCADA interfaces display real-time production data, including belt speeds, depositor accuracy, wrapping count, rejection rates, temperature profiles, and chocolate viscosity. Ingredient dosing is closed-loop controlled. If sugar concentration drifts in the peanut butter mix, the feeder corrects flow automatically. Chocolate viscosity is monitored using inline rotational viscometers. Fill weights are verified by high-speed load cells. Position sensors and servo motors keep all timing synchronized across multiple parallel lines. Each line is designed for continuous operation. Changeovers are handled with tool-less part swaps and automated cleaning sequences. Clean-in-place systems, wash tanks, pipes, and depositors between shifts. Heated caustic detergent is pumped through all product contact lines, followed by a water rinse and final sanitizing flush. Flow rate, contact time, and return temperature are logged and verified automatically. Producing 10 million peanut butter cups requires multiple synchronized lines running at high throughput. A single high-speed line can produce over 1,200 units per minute. 10 such lines operating in parallel generate 720,000 units per hour. In a continuous run, lasting just under 14 hours, the full batch of 10 million is completed. Each cup is mechanically identical. Same chocolate mass, same peanut butter volume, same shell thickness, same twist wrap tightness. The consistency is achieved through calibrated depositor nozzles, servo-actuated plungers, precision-heated tanks, and closed-loop feedback across every stage of production. Key tolerances are maintained. Chocolate fill weight within plus as 0.5 grams, peanut butter center within plus 1 millimeter of alignment, wrap tension within 2%, seal temperature within plus 1.5 degrees Celsius. Rejects are tracked and analyzed automatically to detect trends before they cause system-wide variation. Temperature is crucial. Chocolate crystallization, peanut butter viscosity, cooling tunnel performance. Every step is sensitive to thermal drift. Thermocouples monitor all zones, from tanks to tunnels. If any zone deviates from range, alarms sound and the affected section is automatically adjusted or stopped. From the peanut grinding to the pallet wrap, the process is fully integrated. There are no idle steps. Syrup mixing, shell forming, core deposition, sealing, cooling, inspection, wrapping, cartoning, and palletizing flow in continuous sequence. There is no manual intervention. Everything moves in rhythm, guided by sensors, actuators, and control algorithms. Producing 10 million M&Ms begins at the granule level. Core ingredients like sugar, cocoa mass, cocoa butter, milk solids, corn syrup, and food-grade colorants are delivered in bulk. Each component is unloaded into stainless steel silos, insulated storage tanks, or vacuum-sealed hoppers. From there, Pneumatic conveyors and positive displacement pumps transfer the raw materials into the processing line with exact flow control. Every ingredient is monitored by mass flow meters, auger dosing systems, and load cell integrated vessels to ensure accurate, repeatable input ratios. The first major step is creating the chocolate centers. These are not flat discs to start with. They begin as lentil-shaped chocolate pieces, formed, cooled, and prepared for shell coating. Chocolate production occurs in a multi-step blending and refining system. Liquid cocoa liquor, cocoa butter, and sugar are pumped into a conche. In this high-shear mixing chamber, ingredients are heated and agitated over hours, reducing acidity and moisture while developing flavor. The mass then flows into a 5-roll refiner. This machine crushes the chocolate through narrowing steel rollers until particle size falls below 20 microns, producing the creamy texture needed for M&M's centers. The refined chocolate returns to a second stage conche for additional smoothing. From the conche, the chocolate mass is pumped through jacketed pipes into tempering units. These systems rapidly cycle the chocolate through heating, cooling, and controlled reheating phases, encouraging the formation of stable cocoa butter crystals. Tempered chocolate exits at a tightly maintained viscosity and temperature, ready for molding. The molding system produces the core. Individual chocolate lentils are formed by depositing droplets of tempered chocolate onto a chilled belt. As each droplet lands, it spreads slightly before solidifying into the iconic disc shape. High-speed vibratory tables level and settle each piece before the belt enters a rapid cooling tunnel. Cold air circulates above and below to ensure uniform hardening. Each M&M-sized piece is checked by laser sensors for thickness and diameter tolerance. Once solidified, the chocolate cores are collected into stainless steel bins and conveyed to the panning room. Here begins the defining process. Sugar shell coating through precision, layering in automated panning drums. The panning drums are large rotating cylinders with polished stainless interiors. Thousands of chocolate cores are loaded into each drum. As the drums rotate, a fine mist of sugar syrup is sprayed through atomizing nozzles. The syrup is a concentrated mix of sugar, glucose, and water, heated to remain fluid but not overly thin. The chocolate cores tumble while the syrup coats them evenly. Cold, dehumidified air is blown into the drum chamber to dry each layer. This process is repeated across dozens of cycles. Each round adds a thin sugar layer. The rotation angle, drum speed, airflow, syrup volume, and spray pattern are all programmable and adjusted in real time by feedback systems. The cores grow gradually, layer upon layer, until the shell thickness reaches the target range. Throughout the panning process, non-contact sensors monitor shell diameter growth. Cameras detect shape anomalies or cracks. Any defective units are removed automatically using vibration sorters and size classifiers. After achieving the proper shell thickness, the final stage of the sugar coating is the polishing sequence. Polishing begins with a thin application of carnauba wax and food-grade glaze. These are sprayed inside the rotating drum, creating a slick coating on the sugar shells. Buffing arms inside the drum press and polish the surface as it spins, producing the high-gloss finish M&Ms are known for. The shine is not just cosmetic, it also protects the candy shell from humidity and reduces friction during packaging. Now, the finished M&Ms are conveyed into the color coding system. The distinctive red, yellow, blue, green, orange, and brown shells are not coded one at a time. Instead, batches are divided and each drum is designated for a specific color. Colorant solutions, made from water-soluble dyes and a sugar base, are sprayed into the rotating drum in much the same way as the shell syrup, but in smaller quantities. The dyed layers are dried with a gentler airflow to prevent streaking or pooling. After color coding, another pass of polishing glaze is applied for clarity and shine. After drying, M&Ms are released onto vibrating conveyor belts. These belts sort the pieces, prevent sticking, and align them into single-file lanes for printing. A laser-guided inkjet system prints the signature M on each piece. Optical sensors locate the center of each candy and trigger the inkjet nozzle to fire the white food-grade ink at exactly the right spot. The print dries in under 1 second using forced air and low heat. The print tolerance is within 1 millimeter per piece. Any candy without a printed M or with a misprint is identified by high-resolution cameras and removed from the stream. Printed M&Ms pass through a metal detector that scans for ferrous, non-ferrous, and stainless steel contaminants. They then flow into a check weigher, which confirms the average weight of grouped candies matches the package specification. If the weight falls outside a narrow band, that group is rejected. Now the candies are funneled into packaging units. Depending on the format, single-serve pouches, theatre boxes, tubes, or multi-packs, the M&Ms are guided through volumetric fillers, counting systems, or load cell-based dosing mechanisms. For pouches, horizontal form-fill-seal machines draw roll-fed plastic film, print batch codes, and form it into bags. A vertical chute dispenses a fixed volume of M&Ms into each bag, which is then sealed with a heated jaw. For boxed formats, cartons are formed from flat blanks by a mechanical erecting arm. Pre-grouped M&Ms are poured into the boxes using funnel-shaped hoppers with vibratory feeders to ensure consistent flow. Boxes are sealed using hot melt glue and compressed under pressure for final closure. All packages are marked with laser-etched batch codes and expiration dates as they exit the system. Finished packages move on to conveyor belts toward the robotic palletizing area. Here, industrial robots equipped with vacuum pads pick up multiple units at once and stack them in program formations onto wooden pallets. Slip sheets are inserted automatically for stability. Once stacked, the pallet moves to a stretch wrapping unit. A rotating arm applies plastic film tightly around the load to prepare it for distribution. To reach 10 million units, the process relies on multiple parallel lines. Each high-capacity line can produce more than 2,000 pieces per second. With 10 synchronized lines running continuously, the factory generates 72,000 pieces per second, over 4.3 million per minute. In just under 40 minutes, the full 10 million pieces are completed, each one identical in size, shape, coating, gloss, and print. All steps are governed by programmable logic controllers. The entire factory is coordinated through a distributed control system, with real-time SCADA dashboards showing every variable: syrup viscosity, shell thickness, air humidity, shell growth rate, rotation speed, dye concentration, gloss level, printing accuracy, and package weight. Sensors monitor the production line at every point. Shelling drums use load cells to detect overfill. Thermocouples track temperature inside conchis, tanks, and coating units. Flow meters control syrup delivery. Cameras confirm print legibility. Servo motors handle belt timing, robotic arm movement, and package alignment. Cleaning cycles run automatically between batches. Sugar lines, chocolate tanks, conchis, panning drums, and depositor heads are cleaned using hot, circulating detergent followed by high-pressure rinses. All cleaning steps are validated by chemical conductivity sensors and logged for traceability. The factory layout is linear but modular. Chocolate production, shell coating, coloring, printing, and packaging are linked by buffer zones that allow for surge capacity. If one stage slows, others continue without shutdown. Every section has redundant machinery to allow for changeovers and maintenance. Tolerance ranges are tight. Shell thickness must fall within +0, 15 millimeters. Chocolate center weight must remain within +0.2 grams. Printing alignment cannot vary more than 1 millimeter. Shell color concentration is monitored by spectrophotometers to ensure consistency across millions of pieces. Every variable, from syrup crystallization to drum angle, to print timing is calibrated for absolute uniformity. This level of precision ensures that 10 million M&Ms are not just mass-produced, but identically produced. Each one carries the same shine, the same crunch, the same chocolate-to-shell ratio, and the same instantly recognizable M. From grinding cocoa to molding chocolate, from layering sugar to polishing glaze, from color batching to robotic stacking, the process never stops. The result is a continuous stream of motion, heat, rotation, and control, where every piece, every shell, and every package flows through the system in perfect mechanical choreography. Lollipop production begins with dry granulated sugar and glucose syrup, delivered in bulk into silos and heated stainless steel storage tanks. The sugar is conveyed through screw feeders into a large dissolving vessel. Simultaneously, glucose syrup is pumped through jacketed pipelines to the same vessel. Water is introduced at a controlled rate to create the initial slurry. The temperature is raised to approximately 110 degrees, while agitators rotate to dissolve all solids. The mixture becomes a clear, homogeneous sugar solution. Once the sugar is fully dissolved, the syrup is transferred via gravity or pump into a vacuum batch cooker or a continuous candy cooker. The cooker raises the syrup's temperature to 145 degrees to 150 degrees, while lowering the internal pressure. The reduced pressure allows water to boil off rapidly without degrading the sugars. The syrup thickens into a dense, high Brix mass. Sensors monitor real-time concentration and adjust heat and vacuum accordingly to maintain the target range, typically 98-99% solids. The cooked candy mass exits the vacuum chamber through a heated outlet, either dropping onto a stainless steel cooling table or into a rotary kneading kettle. On the cooling table, scraper arms fold the mass over itself as it cools. Inside the kettle, mixing paddles rotate at set intervals. The temperature drops gradually to about 90 degree cooks. At this stage, flavor oils, acids, colorants, and emulsifiers are added. Dosing pumps inject precise volumes of ingredients based on the batch weight. Mixing paddles distribute the additives evenly throughout the mass while avoiding air entrapment. If a layered or dual-color lollipop is being produced, the candy batch is divided into separate portions. Each portion is flavored and colored independently in separate kettles. A heating jacket maintains each portion at a stable working temperature. When ready, the portions are loaded into a batch former that can extrude them side by side or swirl them together during the rope formation process. Once mixing is complete, the candy is transferred to a rope sizer. The mass is fed into the machine and drawn through a series of sizing rollers that reduce and elongate the bulk mass into a continuous rope of uniform diameter. Each roller pair incrementally reduces the thickness while maintaining roundness. Servo-driven rollers and load cells ensure tension remains steady along the entire length. Inline cameras monitor the rope diameter within plus 0.5 mm tolerance. As the rope advances, it enters the forming section. Here, it is pulled into a rotary die forming machine. This system consists of two steel rollers with precision-cut cavities. As the rope enters the nip point, a stick is inserted from below by a mechanical arm into the soft mass at the exact moment of compression. The die cavities close, shearing the candy rope and forming the lollipop head around the stick simultaneously. Sticks are fed from a vertical hopper onto a horizontal conveyor where they are spaced using star wheels. They travel into the insertion mechanism where grippers or push rods insert them directly into the hot candy as it is formed. The insertion depth, pressure, and angle are all adjustable. Any stick not aligned properly is automatically rejected before contact with the product. After forming, lollipops drop onto a cooling conveyor. The system is divided into zones with progressively lower air temperatures, beginning at around 25 degrees Celsius and dropping to 10 degrees C. Air is circulated through HEPA filters to remove particulates and maintain constant humidity. Cooling takes 5 to 8 minutes, depending on candy size and formulation. The sticks are kept horizontal to prevent gravitational deformation of the still soft candy head. Once fully cooled and hardened, the lollipops enter the wrapping stage. Multiple high-speed wrapping machines operate in parallel. Each machine feeds film from a large roll. Photocells track registration marks to ensure proper logo alignment. Film is cut into pre-sized sheets and fed into the wrapping jaws. Lollipops arrive single file via guide rails and timing screws. As each piece enters the wrapping section, it is met with a film sheet. The candy is centered on the wrapper, and the machine either twist wraps the film at both ends or folds it around the head and seals it with heated jaws and pressure rollers, depending on the wrap style. Speeds reach up to 800 lollipops per minute per machine. Sensors verify the presence of each stick and confirm film seal integrity. If a lollipop is missing a stick, misaligned, or improperly sealed, it is rejected via an air blast or servo diverter. Properly wrapped lollipops are conveyed to a grouping area where they are accumulated for final packaging. Packaging varies depending on format. Some lollipops are bagged in high-speed, vertical form-fill seal machines. The wrapped candies drop into vibratory feeders that portion them into buckets. Buckets empty into a forming tube where plastic film is formed into a bag, filled, and sealed on the top and bottom. Sealing jaws cut and compress the film simultaneously, producing a finished pouch. For tray packs, lollipops are grouped into clusters using a belt divider. Robotic arms or pushers load fixed quantities into cardboard trays or blister packs. Cartoning machines erect the trays, insert the product, and apply hot melt adhesive to seal the cartons shut. Inkjet or laser printers mark each pack with batch codes and expiration dates. Cartons flow to a case packer, where they are grouped and packed into master cartons. Mechanical arms fold the outer box and glue or tape the flaps. These boxes are stacked in layers on pallets by robotic palletizers. The system alternates stack orientation by layer for load stability. Slip sheets are inserted between layers by a vacuum picker. When the pallet is complete, it transfers to a stretch wrapper. A rotating arm or turntable applies a pre-stretched plastic film around the pallet. Wrapping parameters are adjusted based on pallet height, product weight, and load configuration. Once wrapped, each pallet receives a barcode label and is conveyed to the shipping dock. All stages of lollipop production are managed by programmable logic controllers. Every machine, cookers, rope sizers, forming presses, stick inserters, wrappers, and palletizers is integrated into a plant-wide SCADA system. Operators monitor real-time metrics, including syrup concentration, rope tension, cutter timing, seal temperature, stick depth, wrapping accuracy, packaging speed, and output count. Cooking systems are equipped with conductivity probes and pressure sensors. These devices ensure consistent cooking profiles by regulating steam pressure, vacuum levels, and temperature. Flow meters control syrup and water ratios during dissolving. In the cooling tunnel, temperature and humidity sensors maintain conditions within tight limits to avoid surface cracks or bloom on the hardened candy. Line synchronization is maintained through encoder feedback. Rope feed rate, die rotation, and stick timing are adjusted in real time to prevent drift or misalignment. High-speed cameras inspect each lollipop post-forming for symmetry, stick centering, and surface quality. A quality control logic system tracks defect rates and triggers maintenance if thresholds are exceeded. For striped lollipops, colored candy masses are co-extruded through a color stacking head before entering the rope sizer. Stripes are achieved by arranging differently colored masses side by side or spiraling them with twist control. Layer geometry is controlled by adjusting feed angles and rotation during rope pulling. Dual flavor or filled lollipops use concentric forming. An inner core, often a soft center or powdered flavor pocket, is co-deposited during the forming process. Dual extruders feed the core and shell simultaneously through concentric nozzles. The rope is cut and shaped with the filling encased completely inside. Production speed depends on format. A single forming line can produce over 1,000 lollipops per minute. With multiple lines operating simultaneously, output scales into the millions per day. Each system runs continuously with minimal downtime. Quick release tooling and automated cleaning reduce changeover time between flavors or shapes. Cleaning in place systems are installed on all cooking, mixing, and delivery equipment. These cycles run automatically between batches. Hot water flushes remove residual candy. Caustic detergent circulates through tanks, pumps, and piping. A final rinse ensures all surfaces are food safe. The cleaning process is monitored by conductivity sensors and logged by the control system. Sticks are produced off-site to specification and delivered in bulk. Materials range from extruded polystyrene to compressed paper. Before entering the line, sticks pass through a stick inspector with vision sensors to check for length, roundness, and cleanliness. Only compliant sticks are fed into the press. Any deviation beyond plus 0.5 mm in length or 1 gralus of bend results in rejection. Muffin production in a factory begins with the precision handling of core ingredients: wheat flour, granulated sugar, vegetable oil, eggs or egg replacer, milk or whey solids, water, leavening agents, salt, emulsifiers, and flavor additives. All dry materials arrive in super sacks or silo-fed bulk containers. Liquids are delivered in food-grade tankers and pumped directly into insulated holding tanks. Ingredient feeding systems are automated with load cell-equipped silos, volumetric dosing hoppers, and inline mass flow meters that measure and control exact quantities in real time. The mixing process starts in a large-scale planetary or horizontal mixer. Flour is fed from silos through enclosed pneumatic lines. Sugar is metered in by screw feeders. Liquid components, including water, oils, eggs, and emulsifiers, are introduced from jacketed tanks through pressurized dosing pumps. The mixer uses high-torque arms or paddles to fold the batter, and a PLC-based control system sequences ingredient additions based on a time and speed program. Sensors monitor viscosity, temperature, and mixing torque to determine completion. The mixing cycle is designed to develop a consistent batter texture while minimizing gluten overdevelopment. Most muffins use the muffin method, where liquids and dries are blended quickly with minimal agitation. The final batter is thick, glossy, and aerated. Scraper blades clean the sidewalls of the mixing bowl continuously to ensure uniformity throughout the mix. Once mixing is complete, the batter is pumped into an intermediate holding hopper. These hoppers are jacketed to maintain temperature, typically between 18 degrees Celsius and 26 degrees Celsius, and feature slow-speed agitators to prevent separation. The batter is held under light pressure to feed the depositors efficiently and without introducing excess air. Meanwhile, paper muffin cups are dispensed into baking trays by a cup denister. Trays are made from perforated metal or non-stick coated aluminum, often holding 12 to 24 cavities per tray. The trays travel along a conveyor system toward the depositing zone. As each tray enters the depositor station, it is precisely indexed into place by servo-controlled gates. Batter is deposited using multi-nozzle volumetric piston depositors. These depositors operate with individual cylinders that draw and dispense set volumes of batter into each cup. Fill weights are carefully calibrated, typically between 50 and 120 grams per muffin, depending on product specifications. Tolerances are within +1.5 grams. Deposit profiles can be circular, spiral, or domed, depending on desired peak structure. Depositor heads are adjustable in height and spacing, allowing format changes without complete tooling replacement. For muffins with inclusions, such as blueberries, chocolate chips, or nuts, an ingredient dosing unit integrates with the depositor. Inclusions are metered into the batter just before deposition to prevent sinking or damage during mixing. The distribution system uses augers or vibration channels to deliver equal portions into each cup, either layered or blended depending on recipe. Optional toppings are applied at this stage. Streusel, sugar crystals, seeds, or flavored crumbles are dropped by overhead sprinklers or belt feeders. These systems are synchronized with tray motion, using vision sensors to detect cup position and deliver toppings directly onto the surface of each batter portion. Filled trays proceed to the oven. Industrial tunnel ovens, either gas-fired or electric, bake muffins continuously. The oven conveyor moves at a speed determined by product size and bake profile, typically yielding a dwell time of 12 to 18 minutes. Oven zones are independently controlled for top and bottom heat, with precise air circulation to ensure even baking. Core product temperature is monitored using inline thermocouples that pierce random samples. Exit temperature targets typically range from 93 degrees Cs to 98 degrees Cs. Inside the oven, batter rises due to the activation of chemical leavening agents. Steam forms from the water and egg content, expanding air cells and lifting the batter upward. As proteins coagulate and starches gelatinize, the muffin structure is set. Surface coloration and crust formation are controlled by air humidity and sugar content. Once baked, trays exit the oven onto a cooling conveyor. This conveyor is long enough to allow the muffins to cool from above 90 degrees Celsius down to ambient room temperature, usually within 20 to 30 minutes. High volume air blowers accelerate heat dissipation. Muffins remain in their trays during this time to retain shape and prevent sticking to belts. After cooling, muffins are depanned. A pneumatic or mechanical depanner inverts the tray and applies a brief vacuum or finger push to lift each muffin out. The muffin cups remain intact, and the products are transferred onto a belt for inspection. Empty trays are returned via overhead conveyors or underbelt returns to the cup denesting station for reuse. Muffins are now inspected by a vision system. Cameras mounted above and to the side scan each muffin for volume, surface cracks, peak height, and alignment in the paper cup. Any product that falls outside the specification window is diverted by a mechanical pusher or drop gate. Approved muffins continue to the A packaging zone. Packaging formats vary depending on customer needs. Muffins can be individually wrapped, packed in clamshell trays, or sealed into multi-packs. For individual wrapping, muffins are fed into a flow wrapping line. Each muffin enters a forming collar, where film is wrapped around it and sealed using heated rotary crimpers. Longitudinal and cross seals are made with controlled temperature and pressure. Speeds can reach up to 300 muffins per minute per line. For clamshell packing, muffins are guided into a colada, where robotic pick and place arms grip each unit and place it into thermoformed PT trays. These trays are then lidded and sealed with tamper-evident films or snap-on covers. Date and batch codes are printed using thermal inkjet printers. For bulk or food service formats, muffins are loaded into cardboard display trays or placed directly into polyethylene-lined cartons. Cartons are erected from flat blanks using a box erector. Muffins are loaded in rows, either manually assisted or robotically, and the carton is then closed with hot melt adhesive and conveyed toward the palletizer. At the palletizing station, robotic arms equipped with vacuum grippers or mechanical forks stack cartons onto wooden or plastic pallets. Patterns are selected based on case size and distribution route. Slip sheets are inserted every few layers for stability. Finished pallets are stretch wrapped by a rotating arm system and labeled with barcodes and shipping data. All production steps are integrated into a plant-wide control system. Programmable logic controllers coordinate each machine, while SCADA systems provide real-time data on batch progress, line speed, machine temperature, deposit weight, oven humidity, and output count. Operators monitor the entire line from centralized terminals, adjusting set points and diagnosing faults without stopping the process. Ingredient traceability is managed through automated lot tracking. Each ingredient batch is scanned upon entry and linked digitally to every production batch. Finished goods are barcoded and traced back through mixing, depositing, and baking history. If a deviation occurs, the system flags affected pallets and isolates them immediately. Cleaning is performed through a mix of clean in place and clean out of place protocols. Mixing tanks, pipes, depositors, and pump systems are flushed with alkaline detergent followed by a hot water rinse. Baking trays and conveyors are cleaned with steam or dry brushing. Nozzle heads and sensor lenses are wiped with food-safe solvent solutions. Environmental conditions are tightly controlled. The mixing room is temperature stabilized to avoid batter inconsistency. The depositing area uses filtered air to keep particles off open trays. Oven exhaust is captured and scrubbed. Packaging areas are overpressurized with filtered air to minimize dust entry. Air knives and vacuum hoods remove crumbs during transfer points. If muffins are frozen, post-production, they are conveyed directly into a spiral freezer. Cold air at 35 degrees Celsius rapidly reduces product temperature to below 18 degrees Celsius within 30 minutes. Frozen muffins are then flow wrapped or shrink wrapped in bulk, palletized, and moved into cold storage. The entire process is timed to avoid moisture condensation and surface bloom. Shape consistency is enforced at multiple stages. During depositing, laser sensors measure batter height. Post-baking, peak height and crown diameter are scanned optically. Deformed or underfilled units are rejected before reaching packaging. Automated systems collect real-time statistics to maintain statistical process control. The production line is modular. Deposit heads, paper cup sizes, and topping applicators can be changed within minutes. Oven belts, mixing times, and wrap formats are selected through the control interface. Recipe memory allows for instant switchovers without manual recalibration. Muffin factories operate continuously, running multiple shifts with minimal stoppages. High-volume lines produce tens of thousands of muffins per hour. Every unit is created through thermal transformation, timed chemistry, pneumatic forming, and servo-synchronized packaging. Every process step is calibrated, controlled, and monitored to meet exact physical and sensory specifications. The factory production of chocolate chip cookies begins with the bulk delivery of essential raw ingredients. These include wheat flour, white and brown sugars, vegetable shortening or butter substitute, liquid eggs or pasteurized egg products, chocolate chips, leavening agents, salt, emulsifiers, water, and flavorings such as vanilla. Dry ingredients like flour and sugar arrive in super sacks or silo containers and are transferred pneumatically or via screw conveyors into batching silos. Liquid ingredients are stored in temperature-controlled stainless steel tanks connected to dosing lines. Chocolate chips are stored in insulated bins and gently agitated to prevent compaction or melting. Automated ingredient handling systems prepare each batch according to a programmed recipe. The process begins in the scaling room or dosing station, where load cells measure and release precise amounts of dry and wet ingredients into transport hoppers. Materials are conveyed into a high-capacity horizontal mixer, typically of the ribbon or paddle variety. These mixers are equipped with dual-axis blades and variable speed motors. Ingredients are added in a fixed sequence. Fats and sugars first to cream, then eggs and water, followed by dry powders, and finally chocolate chips. Mixing proceeds through defined phases. During the creaming phase, sugar granules break down the fat, creating air pockets essential for cookie spread and tenderness. The incorporation of eggs and water creates an emulsion that stabilizes the dough. As flour and leavening agents are added, the blades slow down to avoid overdevelopment of gluten. The chocolate chips are added last and folded gently to prevent breakage. Inline torque sensors monitor dough consistency, and viscosity meters verify proper development. Batch temperatures are maintained between 18 degrees Celsius and 24 degrees Celsius to prevent fat melt and preserve dough structure. Once mixed, the dough is transferred into a hopper positioned above the forming line. Dough moves via auger or vacuum feed into a volumetric portioning system. A rotary cutter or wire cut depositor divides the dough into individual pieces, each weighing between 25 and 50 grams, depending on the product specification. The depositor uses servo-driven pistons to extrude dough pieces onto a moving steel mesh or Teflon-coated band conveyor. Optical sensors monitor spacing, alignment, and shape, correcting for drift in real time. For wire-cut lines, dough is pushed through nozzles and sliced cleanly by a fast-moving wire as the band advances. For rotary molded formats, dough is pressed into engraved molds on a rotating drum, then released onto the band using a flexible scraper blade. Shape, weight, and chip distribution are confirmed by an overhead vision inspection system using laser profiling and high-speed imaging. Defective pieces are automatically rejected via air puffs or diverter gates. Decorative or functional toppings, such as extra chocolate chips, coarse sugar, or sea salt, can be added before baking. These are applied using vibratory feeders or pneumatic dispensers, synchronized with the conveyor speed. Toppings are placed with positional accuracy, controlled by encoder feedback. The unbaked cookies enter the oven on a continuous conveyor. Most large-scale bakeries use tunnel ovens ranging from 25 to 60 meters in length. Ovens may be gas-fired, electric, or hybrid, and are divided into multiple heating zones. Each zone has independently controlled top and bottom heating elements, recirculating fans, and steam injection systems. Bake times range from 6 to 12 minutes, depending on cookie size, dough moisture, and desired texture. As cookies pass through the oven, heat activates the leavening agents, causing the dough to expand. Water turns to steam, fats melt, and proteins begin to coagulate. Sugars caramelize on the surface, contributing to flavor and browning. Top heat ensures color formation, while bottom heat ensures base firmness. An inline thermal imaging system monitors surface temperature and identifies any uneven baking. Oven humidity is also regulated to manage cookie moisture and bite texture. After baking, cookies exit the oven at internal temperatures above 90 degrees Celsius. They are transferred to a multi-tiered cooling conveyor that spans 20 to 40 meters in length. Cool ambient air is blown across the surface of the cookies to gradually reduce their temperature to 30 degrees or lower. The cooling line uses stainless steel or open mesh plastic belts to allow airflow from above and below. Rapid cooling is avoided to prevent cracking or structural collapse. Crumb blowers and air knives remove any loose particles generated during baking. Once cooled, cookies pass through a final inspection station. A high-speed vision system checks each unit for diameter, thickness, browning level, chip exposure, and edge uniformity. Any cookie failing the inspection parameters is ejected automatically. Passing cookies proceed to the packaging section. Depending on the final format, cookies may be packed in flow wrap, trays, clamshells, or flexible pouches. For flow wrap, cookies are aligned single file by a lane guide and transferred onto film. Film is unwound from a roll, cut to length, and wrapped around each cookie. heat-sealing jaws close the ends and form a longitudinal seam. Wrapping speeds can exceed 500 cookies per minute per lane. For tray packing, cookies are collated into rows by a bucket conveyor and placed into pre-formed plastic or paperboard trays by robotic pickers. In multi-pack formats, cookies are stacked vertically or nested side by side using servo-driven stackers. These stacks are inserted into pouches or boxes that are formed, filled, and sealed in a continuous motion machine. Machines apply nitrogen flush to pouches before sealing to displace oxygen and extend shelf life. Date codes and batch numbers are applied using thermal inkjet printers or laser coders. Barcodes are printed for inventory and traceability. Wrapped products are collated into cartons by robotic arms equipped with suction grippers. Cartons are sealed with hot melt glue and stacked onto pallets in pre-programmed patterns. Palletizers use multi-axis robots with slip sheet dispensers to build stable, shippable loads. Pallets are conveyed to a stretch wrapper where they are secured with plastic film. Labels with tracking codes and distribution information are applied before pallets are moved to dispatch or cold storage. All stages of production are monitored and controlled by a centralized PLC-based automation system. The entire factory line is integrated through SCADA interfaces that provide operators with real-time dashboards showing mixer status, dough temperature, line speed, oven zone profiles, moisture content, wrapping rate, and defect counts. Recipe management software ensures every batch conforms to specification and every change is logged digitally. Clean-in-place systems are used for all dough contact equipment. After production, mixers, hoppers, pipelines, and depositors are flushed with food-safe detergent and rinsed with hot water. Belt surfaces are cleaned with steam or sanitizing solution and scraped with mechanical blades. Oven interiors are brushed and vacuumed between shifts to remove carbonized residue. Environmental conditions like air pressure, temperature, and humidity are tightly controlled in all processing zones to prevent microbial growth and maintain dough stability. Ingredient traceability is maintained through barcode scanning and batch logging. Each input is recorded upon arrival and linked to its corresponding finished batch. If any quality issue is detected downstream, affected products can be isolated immediately through backtracking. Quality assurance teams conduct routine sampling, including water activity, texture, chip dispersion, packaging seal integrity, and shelf life simulations in controlled chambers. Some facilities operate in robing lines for chocolate-dipped or striped cookies. These cookies exit the oven and are passed through a tempering tunnel where they receive a coating of milk, dark, or white chocolate. The coating is applied using cascading curtains or rotating drums, followed by a cooling tunnel with airflow designed to produce a glossy finish and stable crystallization. Other variants include filled cookies, where dough is extruded with a central cavity filled with chocolate paste, caramel, or fruit gel. These are formed using a co-extrusion head that aligns both dough and filling. The filled ropes are cut by guillotine or rotary blades and shaped prior to baking. Additional vision inspection ensures filling is centered and not leaking. Lindt chocolate is produced in a tightly structured factory process that begins with the transformation of raw cocoa beans into ultra-fine, smooth, and creamy chocolate using specialized machines, proprietary techniques, and finely tuned timing sequences that preserve the delicate flavors of cocoa while eliminating bitterness and grit. The process begins when whole dried cocoa beans arrive at the factory in large bulk containers and are conveyed directly into storage silos built to maintain low humidity and a stable temperature to prevent any premature oxidation or moisture absorption. From these silos, the beans are measured out by weight and directed into a cleaning unit where vibrating screens, air classifiers, and magnetic separators remove stones, dust, string, and any foreign matter, so that only clean beans proceed to the next step. The cleaned cocoa beans are then transferred to a batch roaster or continuous drum roaster, which exposes them to dry hot air with precise temperature control and rotation speed to ensure the beans are heated evenly from all sides. Roasting develops the flavor of the cocoa, reduces astringency, and darkens the color of the nibs inside the shell. The temperature and duration of roasting are carefully controlled depending on the variety and origin of the bean, and are adjusted based on moisture content and desired flavor profile. Once roasted, the beans are cooled rapidly using forced air to prevent over-roasting, and then they move to the winnowing machine. The winnowing process cracks each roasted bean and separates the outer shell from the nibs inside. This is done using mechanical rollers that crush the beans gently, and blowers that blow away the lighter shells while heavier nibs fall into collection bins. The winnowed nibs are what contain the cocoa solids and cocoa butter required for chocolate production. These nibs are directed into large grinding chambers where rotating steel drums or stone rollers crush them into a thick, dark, gritty paste known as cocoa liquor. This liquor is then pumped into a series of high-pressure hydraulic presses that separate the fat from the solids. The fat becomes cocoa butter, while the remaining cake is pulverized into cocoa powder. In parallel, whole milk powder, sugar, and additional cocoa butter are stored in bulk hoppers and prepared to be added to the chocolate base. The exact formulation depends on whether the chocolate being made is milk, dark, or white. For milk chocolate, cocoa liquor is blended with sugar, milk powder, and cocoa butter in large horizontal mixers until a uniform paste forms. This coarse chocolate mass is then sent to the refining stage. Refining involves passing the chocolate paste through a sequence of steel rollers that reduce particle size. Each roller set progressively narrows the gap, crushing sugar crystals and milk particles until they are reduced to between 15 and 20 microns. This ultra-fine particle size is critical for the mouthfeel of Lindt chocolate, ensuring there is no graininess when the chocolate melts on the tongue. The refined chocolate then moves to the conching stage, which is one of the defining steps in Lindt production. Conching is done in elongated mixers called conches that slowly knead the chocolate at elevated temperatures, typically between 45 and 80 degrees Celsius, for several hours or even days, depending on the recipe. The purpose of conching is to develop flavor and texture. During this phase, volatile acids and off flavors are driven off by heat and agitation, while the friction created by the mixing reduces viscosity and smooths the fat dispersion. This stage also transforms the aroma profile, eliminating any lingering bitterness or sharp notes and rounding out the flavor. In Lindt's process, conching is considered both a science and an art, and the parameters are adjusted delicately to reflect the cocoa origin, sugar type, and desired smoothness. Once the chocolate mass has reached the optimal flavor and flow characteristics, it is transferred to tempering machines. Tempering is a controlled heating and cooling cycle that aligns the cocoa butter crystals into a stable form known as form Vi. This ensures that the finished chocolate will have a glossy finish, a crisp snap, and will not develop bloom or grayish streaks over time. In the tempering machine, the chocolate is first heated above the melting point of all cocoa butter crystals, then cooled to a point where only form 5 can reform, and finally reheated slightly to working temperature. During this process, precise control of temperature and agitation is vital. Tempered chocolate is now ready for molding or enrobing. For bar production, tempered chocolate is poured into polycarbonate molds, which are vibrated on automated shakers to remove air bubbles and allow the chocolate to settle evenly into every corner. The molds are then passed through cooling tunnels, where cold air gradually lowers the chocolate temperature until it sets and solidifies. For filled chocolates or truffles, The molds may first receive a thin shell of chocolate, which is cooled and then filled with soft centers like ganache, praline, or liqueur before being sealed with more chocolate and cooled again. Once the chocolate has solidified, the molds are inverted and gently flexed by mechanical arms or vibration plates to release the bars or pieces. These are conveyed through a final inspection area where high-speed cameras and vision systems scan for imperfections such as broken corners, air pockets, or deformed logos. Defective. Pieces are rejected automatically, and perfect pieces proceed to wrapping. Wrapping is tailored to the product type. Lindt bars are typically wrapped in foil, followed by an outer paper sleeve. Machines cut foil to precise dimensions, fold it tightly around each bar, and then apply the paper wrapper using hot glue or pressure-sensitive rollers. Filled chocolates and balls are often wrapped in twisted foil ends or sealed flow packs using high-speed rotary packaging machines. Each wrapped unit is date-coded and batch-labeled for traceability. The wrapped chocolates are grouped into cartons by robotic arms that use suction cups to pick and place items into retail display boxes or shipping trays. Cartons are sealed, labeled, and palletized on automated stations where stretch wrap secures the load for transport. Pallets are scanned, assigned barcodes, and stored in climate-controlled warehouses to preserve flavor and appearance. The ambient temperature is maintained between 15 and 18 degrees Celsius with low humidity to prevent sugar or fat bloom from forming. Throughout the entire process, every parameter, from roast temperature to concha duration to tempering curve, is logged and monitored by a central control system. Inline sensors track viscosity, temperature, and particle size, while samples are pulled regularly for lab testing. These lab tests include moisture content, flow behavior, flavor analysis, and crystal structure confirmation to ensure the chocolate meets Lindt's quality standards. Chocolatiers also perform sensory evaluations, tasting samples for balance, aroma, melt, and finish. Hygiene and cleaning are equally critical in the production line. Chocolate making equipment is cleaned between product changes using melted cocoa butter flushes, which push out remnants of previous batches, followed by food-grade detergent cycles and high-pressure rinse systems. All cleaning is validated with swabs and lab tests to prevent flavor, cross-contamination, and microbial growth. In factories producing multiple chocolate types, changeovers are scheduled with precision to minimize downtime. Dark chocolate lines are usually run first, followed by milk, and then white chocolate, since darker varieties are more difficult to flush from equipment. Any chocolate not meeting specification during changeover is reworked or diverted to non-retail uses. Each ingredient in Lindt chocolate is treated with care. Sugar is milled to uniform crystal size and stored in dry silos with dehumidifiers. Milk powder is kept in oxygen barrier bags to preserve freshness. Cocoa butter is melted and filtered through fine mesh screens to remove impurities before blending. Even inclusions like nuts or fruit are roasted or candied on site to preserve their crunch and freshness. And they're added via gravity feeders that deposit precise amounts into the mold as chocolate flows in. The finished product that arrives on shelves results from a careful sequence where every gram of chocolate has passed through dozens of machines, heat cycles, mixing steps, and quality gates to guarantee it matches Lindt's profile for shine, snap, aroma, and flavor. From bean to bar, the chocolate moves with purpose through a network of conveyors, tanks, rollers, pumps, sensors, and skilled calibration, ensuring that what ends up in the foil wrapper is not just chocolate, but a refined and deliberate experience. Hershey's chocolate is manufactured through a large-scale factory process that transforms raw agricultural ingredients into solid molded chocolate bars, using a continuous sequence of heating mixing, refining conching, tempering molding, and packaging that is engineered for consistency, scale, and shelf life. The process begins with the intake of whole, dried fermented cocoa beans that are sourced in bulk and delivered in freight containers to the processing facility, where they are offloaded using vacuum conveyors or bulk tipping systems into steel silos designed for moisture protection and temperature stabilization, so the beans are kept in ideal condition before production begins. From these silos, the beans are moved into a cleaning station, where mechanical sieves, air separators, and magnetic traps remove foreign matter such as twigs, dust stones, and bits of string. And the cleaned beans then enter large batch roasters or continuous flow roasting drums, where hot air is circulated through the rotating chamber to heat the beans evenly and activate the chemical changes responsible for chocolate flavor and aroma. The exact roasting temperature and time are carefully controlled to vary the flavor strength depending on the blend being produced, and the roasted beans are then cooled quickly using forced air or vacuum systems to lock in the desired profile and prevent overdevelopment. Next, the cooled roasted beans pass through a cracking and winnowing machine where roller blades break the shells apart, and airflow systems separate the lighter papery husks from the heavier cocoa nibs, which contain the actual cocoa solids and cocoa butter required for chocolate production. The separated nibs are collected and sent to grinding chambers, where heavy granite rollers or steel grinders crush them into a thick, dark paste known as chocolate liquor, which is not alcoholic but simply refers to the pure ground state of cocoa solids suspended in their own fat. At this stage, the chocolate liquor is held in heated storage tanks, where it can be separated into cocoa butter and cocoa solids if necessary, using hydraulic presses or used directly in chocolate mass formulation. The chocolate base used for Hershey's milk chocolate typically includes chocolate liquor, sugar milk, powder, cocoa butter, and sometimes emulsifiers to improve flow properties. And in this stage, these raw materials are measured precisely using load cells and volumetric dosing systems before being transferred into industrial blenders, where they are mixed at high speeds into a coarse brown paste. The sugar crystals are still relatively large at this point, and the milk powder has not fully hydrated, so the mixture is lumpy and thick. But the goal of this step is to distribute the ingredients uniformly before refining. The refining process consists of passing the chocolate paste through a 5-roll mill or similar refining system, which crushes and shears the mixture repeatedly until all particles are reduced to between 15 and 20 microns in size, which is below the threshold of perception on the human tongue and is responsible for the smooth texture of finished chocolate. The refined powdery mass exits the rollers as dry flakes, which are collected and fed into large conching vessels, which are long horizontal mixers with heavy paddles that knead the chocolate continuously while applying gentle heat. Conching is one of the most important steps in the process and can last from several hours to a full day, depending on the batch size and the desired flavor characteristics. And during conching, the frictional heat softens the cocoa butter, allowing it to coat sugar and milk particles completely, while the mixing action evaporates unwanted volatile acids that contribute bitterness and also promotes chemical bonding between ingredients that gives chocolate its rounded flavor and creamy mouthfeel. In Hershey's process, this stage may include the addition of flavor compounds or the use of proprietary heating profiles that contribute to the distinctive, sweet, slightly tangy note associated with their milk chocolate. After conching, the now liquid chocolate mass is pumped through a fine mesh filter to remove any remaining solids, and then enters the tempering system, which is a temperature-controlled series of heat exchangers and holding tanks that bring the chocolate through a controlled heating and cooling cycle designed to stabilize the cocoa butter crystals into the desired form V structure, which provides gloss snap and resistance to fat bloom. The tempering process requires careful monitoring of viscosity temperature, shear rate, and time to produce a chocolate that will remain stable during storage and distribution. Once tempered, the chocolate is moved into the molding line, where it is dispensed into bar molds using precise portioning heads that fill each cavity to the exact weight required. And the filled molds are shaken on vibrating tables to eliminate air bubbles and ensure even distribution of the chocolate across the mold. The molds then pass through a cooling tunnel where refrigerated air is circulated in stages to gradually bring the chocolate down to the release temperature, allowing it to solidify without developing stress cracks or surface bloom. When the chocolate has fully set, the molds are inverted and the bars are ejected using mechanical arms or flexing systems that pop the finished bars onto conveyor belts for inspection. Every bar passes under a series of vision systems that scan for surface defects, broken edges, misaligned logos, or irregular thickness, and any bar that fails inspection is automatically diverted for rework. Acceptable bars move forward to the wrapping section, where high-speed machines fold foil or film around each piece and seal it using heat or pressure depending on the packaging format. Paper sleeves or cardboard cartons are then applied and printed with product information barcodes and expiration dates using inline inkjet or laser printers. Wrapped bars are grouped into shipping cases by robotic packing arms and loaded onto pallets, which are stretch wrapped and labeled for traceability before being moved into temperature-controlled storage rooms maintained between 15 and 20 degrees Celsius to preserve texture and flavor. From this point, the bars are distributed through refrigerated trucks or ambient carriers depending on shelf life and destination requirements. In parallel with production, the entire process is monitored by sensors that record key data at every stage, from ingredient weight and tank temperature to roller pressure and mold cavity fill speed. And this data is fed into a centralized quality control platform that logs all production variables and triggers alerts if any parameter drifts outside the approved range. Quality assurance teams sample bars from each batch and test them in laboratories for moisture content, melt profile, flavor, strength, hardness, and microbiological stability. And these tests ensure that every bar maintains the same quality level regardless of where or when it is produced. All equipment used in the chocolate production line is constructed from food-grade stainless steel and is subject to strict sanitation protocols between product runs. Clean-in-place systems flush liquid chocolate from pipes and tanks using melted cocoa butter, followed by hot detergent solutions and sterile water rinses. And these cleaning cycles are verified using swab tests and microbial analysis before the next production run begins. During cleaning, mechanical components such as belts, pumps, and seals are inspected for wear and lubricated with food-safe oils to maintain performance and prevent contamination. Because Hershey produces multiple chocolate types, including dark white and flavored variants, the factory must perform regular changeovers that are scheduled with precision to minimize waste and avoid flavor crossover. And this is typically done by running from the lightest product to the darkest, so that any residual ingredients are less likely to impact flavor in the next batch. Storage of ingredients is just as critical as processing, and milk powder is kept in dehumidified silos lined with oxygen barriers, while cocoa butter is stored in heated jacketed tanks that maintain a constant liquid state, and sugar is held in dry bins fitted with vibratory feeders to ensure consistent flow into the mixers. Even inclusions like almond toffee or cookie pieces are added through dedicated feeders designed to introduce solids at the molding stage without disrupting flow or causing jams. From beginning to end, Hershey's chocolate production line is a finely tuned balance of mechanical engineering, food science, and sensory evaluation, where the transformation of beans into bars depends on maintaining strict control over texture, flavor, and structural integrity. The iconic bars that result are the outcome of thermal history particle refinement, fat crystallization, and packaging precision that together produce a chocolate that is consistent across millions of units and recognized by consumers around the world. Godiva chocolate production begins with the careful handling of raw cocoa beans, which arrive at the factory in bulk loads from cocoa growing regions, and are stored in cool, dry silos that prevent moisture contamination, oxidation, and pest activity. These beans are first cleaned through mechanical sifters that remove stone shells dust and organic debris using a series of vibrating screens, suction fans, and magnetic traps. Once cleaned, the beans are weighed and portioned by automated systems and conveyed to the roasting chambers, which are precision-engineered rotating drums capable of uniform thermal penetration across the entire mass of cocoa beans. Roasting is the first flavor-developing stage in the chocolate-making process, and in the Godiva production method, it is carried out at moderate temperatures for extended periods, which helps preserve the aromatic volatiles while driving off unwanted acidity and bitterness. Each batch is roasted based on its origin and moisture level, with constant temperature regulation using internal thermocouples that feed data to a computerized control system. Once the beans are fully roasted, they are immediately cooled with forced air systems that halt the roasting curve and stabilize the volatile compounds formed during heating. The next step is winnowing, which involves cracking the roasted beans open to separate the brittle shells from the cocoa nibs inside. The beans pass through a mechanical cracker that gently fractures them, and a pneumatic winnower that blows the lighter shells away while the heavier nibs fall into collection bins. These nibs are the core ingredient in all chocolate and contain both cocoa solids and cocoa butter in their natural ratio. The nibs are routed to a pre-grinding unit where rotating stone rollers or steel discs crush them into a thick, gritty paste known as cocoa liquor. This liquor is heated slightly to reduce viscosity and then transferred to high-pressure hydraulic presses that squeeze out the cocoa butter, leaving behind a dense cake of compressed solids which are ground into cocoa powder. For milk chocolate production, the cocoa liquor is blended with refined sugar, high-quality milk powder, additional cocoa butter, and in some recipes, a hint of vanilla or lecithin, which acts as an emulsifier. Each ingredient is dosed using gravimetric feeders and poured into large, high-speed mixers where they are combined into a smooth, uniform brown paste. This initial chocolate mass is far too coarse to be palatable, so it is sent to the refining system. This consists of a 5-roll mill where the mixture passes between sets of rollers that progressively reduce the particle size down to below 20 microns, creating a texture that feels smooth and creamy on the tongue. After refining, the powdered chocolate mass is transferred into conching machines, which are large horizontal vessels with internal mixing blades that work the chocolate slowly while applying gentle heat. This process can take anywhere from 12 to 24 hours, depending on the desired flavor profile, and is critical for developing the smooth texture, deep aroma, and balanced flavor that distinguishes Godiva from other mass-market chocolates. The conching action evaporates undesirable acids and moisture while distributing the cocoa butter evenly over every particle, which contributes to the distinctive mouthfeel and melt of the final product. Once conching is complete, the chocolate is sent through a filtration unit to remove any remaining impurities and then proceeds to the tempering stage, which is one of the most technically precise parts of the entire process. Tempering involves heating the chocolate to above its melting point, then cooling it down to initiate the formation of stable cocoa butter crystals known as Form 5, and then slightly reheating it to a working temperature, where those crystals can be maintained in suspension. This controlled crystallization ensures that the finished chocolate will have a glossy sheen, a crisp snap when broken, and a long shelf life without the development of sugar or fat bloom. The entire tempering process is carried out in enclosed stainless steel tanks equipped with agitators and digital thermostats that keep the temperature profile exactly within a 1-degree tolerance. The tempered chocolate is now ready for molding or enrobing. For solid chocolate bars or shapes, the tempered chocolate is poured into precision-engineered molds made of food-grade polycarbonate. These molds are vibrated to remove air bubbles and ensure that the chocolate spreads evenly into every corner and detail of the design. The filled molds then pass through a cooling tunnel that gradually lowers the temperature, allowing the chocolate to solidify and contract slightly so it can release cleanly from the mold. The pieces are then turned out and conveyed to the packaging line. For filled chocolates like pralines, truffles, and caramels, the process adds additional steps. The mold is first coated with a thin layer of tempered chocolate using spinning or tilting mechanisms to create a uniform shell. This shell is cooled just enough to firm up and then filled with liquid centers like ganache hazelnut paste or fruit cream using precision nozzles that deliver exact volumes to each cavity. Once filled, the chocolates are sealed with a final layer of chocolate and sent through a second cooling tunnel to solidify completely. These filled chocolates are then demolded and sent to wrapping. Enrobed chocolates, such as chocolate-covered nuts or biscuits, are passed on a conveyor belt under a waterfall of tempered chocolate where they are coated completely and pass under a vibrating plate that ensures even coverage and allows excess chocolate to drip off. The enrobed pieces then pass through a cooling tunnel similar to the molded chocolates where the coating solidifies uniformly. Wrapping is carried out using high-speed automated systems that use foil or flow wrap depending on the product. Each chocolate is first wrapped in an inner layer to preserve freshness and then given an outer wrap or box depending on whether it's a single piece or part of a collection. These wrappers are applied using thermal sealers and folded precisely by mechanical arms to maintain presentation quality. The finished chocolates are grouped into assortments using pick-and-place robots that load them into rigid trays or decorative boxes, which are then closed, labeled, and shrink-wrapped for transport. Throughout the entire production process, quality control is integrated into every stage. Inline sensors measure parameters like particle size, viscosity temperature, and moisture content. Random samples are taken and tested for flavor consistency, flow behavior, microbiological safety, and visual appearance. Each batch is tracked from bean to box using barcode systems and digital batch records, which allow full traceability and accountability. Any deviation from the strict specifications results in automatic rejection and investigation to maintain the high quality associated with Godiva. Packaging lines are designed not only for speed, but also for delicate handling. Chocolates are not simply dropped into boxes, but placed gently by grippers or vacuum arms to prevent any scuffing or deformation. Seasonal and limited edition boxes are assembled by dedicated packaging stations that include decorative inserts, gold leafing, or ribbon application, all of which are coordinated with the central production database to match inventory with demand forecasts. Finished products are palletized automatically and moved to cold storage areas where the ambient temperature is held between 15 and 18 degrees Celsius with low humidity to protect against fat bloom sugar crystallization or flavor degradation. Logistics systems monitor inventory in real time and coordinate dispatch using climate-controlled vehicles that ensure the chocolates arrive at retail destinations in pristine condition. Factory sanitation is handled with clean-in-place systems for all enclosed equipment and rigorous manual cleaning protocols for all external surfaces. Between product types, especially when transitioning from dark to milk or white chocolate lines, are flushed with cocoa butter and inspected using allergen tests to confirm no cross-contamination occurs. Equipment such as molds, tempering tanks, and piping is made from food-grade stainless steel and is subject to frequent validation, including swab tests, microbiological plating, and ATP analysis. Each product that leaves the factory reflects a meticulously controlled combination of mechanical design, sensory expertise, thermal precision, and ingredient handling, all executed on a scale that allows handcrafted quality to meet global demand. Godiva's reputation depends on this balance where artistry meets automation, where every bar and truffle is not only shaped by steel and steam, but guided by formulas and feedback that ensure every box offers the same refined, luxurious experience no matter where it is opened. Dairy Queen ice cream begins with the formulation of a liquid ice cream mix that contains a specific balance of milk solids, butterfat, sweeteners, stabilizers, and emulsifiers, all designed to create a product with a soft serve texture, rich flavor, and the structural integrity to hold shape when dispensed at below freezing temperatures. The process starts with the metering of liquid ingredients into a high-capacity stainless steel mixing tank. Milk, cream, and liquid sweeteners, such as corn syrup, are pumped from refrigerated storage tanks using automated pumps that are controlled through a programmable logic controller system. The precise volumes are determined by batch recipes that are stored digitally and loaded into the mixing unit via operator interface panels. Dry ingredients like skim milk powder, dextrose, and stabilizer emulsifier blends are added through a dry powder feeder positioned over the mixing tank. As the powders are introduced, high-speed impellers and rotor-stator mixers circulate the mixture, dispersing solids uniformly and ensuring the base is homogeneous. This initial mix is agitated continuously for a set period until the solution reaches a uniform temperature and particle distribution. Once mixed, the liquid ice cream base is pumped through a series of inline filters to remove any clumps, undissolved particles, or foreign matter before proceeding to the pasteurization stage. Pasteurization is a critical thermal process that ensures microbiological safety and improves the mix's ability to support uniform freezing and aeration. The base mix is pumped through a plate heat exchanger system, which uses hot water or steam on one side of the stainless steel plates and the ice cream mix on the other. The two fluids never touch, but heat is transferred efficiently across the metal surfaces. The mix is quickly heated to a target temperature, typically around 80 to 85 degrees Celsius, and held at that temperature for a predetermined number of seconds, usually no more than 25, before being rapidly cooled to below 4 degrees Celsius using chilled water or glycol solution in the next section of the exchanger. The rapid heating and cooling prevent unwanted protein denaturation while killing potential pathogens. The chilled, pasteurized mix is then transferred to an aging tank. These tanks are large, insulated stainless steel vessels equipped with slow-speed agitators that maintain gentle circulation without incorporating air. The mix is aged for a minimum of 4 hours, often overnight, to allow the fat crystals to partially solidify and the stabilizers and emulsifiers to fully hydrate. This aging process improves body, creaminess, and melt resistance of the final product and ensures a consistent structure when the mix is frozen later. After aging, the liquid mix is pumped into a continuous freezer. This is where the transformation from liquid to frozen soft serve occurs. The continuous freezer is a high-efficiency, jacketed stainless steel cylinder containing a rotating scraper blade assembly and a direct expansion refrigeration jacket filled with ammonia or another refrigerant. As the mix enters the chamber, it is chilled to approximately 6 to 8 degrees Celsius while being whipped rapidly by the rotating blades. This mechanical action accomplishes two things at once. It freezes the water content of the mix into fine ice crystals and incorporates air into the structure to create overrun. Overrun is the term used to describe the volume of air introduced into ice cream, expressed as a percentage of the original mix volume. Dairy Queen soft serve typically has a controlled overrun around 45%, meaning 100 liters of base mix will become 145 liters of finished product. This air is crucial for texture, mouthfeel, and lightness. It is injected through filtered nozzles as the blades churn the mixture. The balance of air and ice must be tightly regulated. Too much air leads to foaminess, while too little creates a heavy, dense product that doesn't dispense smoothly. The frozen, aerated soft serve exits the continuous freezer at a semi-solid state and is transferred immediately into sterile holding tanks, or directly into distribution containers, depending on the factory design. In larger operations, the soft serve may be pumped into pre-chilled, bag-in-box containers made of multi-layered, food-safe plastic film that protects the product from light and moisture. Each bag is filled by volume through a no-drip valve, sealed mechanically, labeled with a production code and expiration date, and moved to refrigerated storage. In other systems, the soft serve may be routed into pressurized stainless steel kegs or bulk plastic drums equipped with quick connect couplings for easy installation at the retail dispenser level. These containers are filled in clean rooms under positive pressure airflow to eliminate airborne contamination. The filled containers are immediately stored at sub-zero temperatures in blast freezers or walk-in cold rooms set to maintain the product just below the freezing point without hardening the mix entirely. From here, the frozen product is shipped in refrigerated trucks to the point of sale, typically a retail location equipped with a dedicated soft-serve dispensing machine. These machines are miniaturized versions of the industrial continuous freezer used in the factory. Each machine contains a hopper that holds the soft-serve mix, an auger or scraper blade assembly, and a narrow freezing cylinder cooled by either air or water-based refrigeration systems. When the machine is activated, the product is pulled from the hopper into the freezing cylinder, where it undergoes a final freezing and aeration stage. The mix is chilled further to about 9 degrees Celsius, while the blades whip it to preserve consistency. When the lever on the dispenser is pulled, the pressurized frozen product is extruded through a specially designed nozzle that imparts the signature spiral swirl to the ice cream as it is dispensed into a cone or cup. Each part of this process, from raw milk to cone, relies on tightly controlled mechanical parameters, time-sensitive transitions, and a closed system design that ensures the finished Dairy Queen soft serve has a consistent texture, smooth pour, and creamy mouthfeel. The cooling cycles, flow rates, agitation speeds, syrup-to-air ratios, and thermal profiles are all digitally monitored at every stage using PLCs, sensors, thermocouples, and SCADA systems. Adjustments are automated to keep the output within strict tolerances. To ensure quality, samples are pulled at multiple points in the process for physical, chemical, and microbiological testing. These include fat content analysis using infrared spectroscopy, overrun verification using displacement methods, viscosity measurement through flow cups or rotational viscometers, and sensory testing by trained tasters who evaluate mouthfeel, melt profile, sweetness, and aftertaste. Sanitation procedures are carried out daily or between batches. All pipes, valves, hoses, and tanks in the mix production system are cleaned in place using automated CIP systems that cycle through pre-rinse, caustic wash, acid rinse, and final sanitizing steps. Soft serve dispensers at the retail level are cleaned manually with specialized brushes and food-safe detergents, followed by complete reassembly and sanitization with hot water flushes to ensure hygiene is maintained without altering the flavor of future batches. Every production batch is traceable by date, time, machine, operator, and ingredient lot, logged in a database that allows for immediate traceback in case of any quality issues. Digital records are kept for regulatory compliance and internal process optimization, helping to refine recipes, extend shelf life, and reduce variability between runs. Bluebell ice cream production begins with the assembly of the ice cream base, which is the liquid foundation used to create every flavor. This base must be smooth, homogeneous, microbially safe, and physically stable throughout the freezing, hardening, and distribution stages. To prepare it, the process starts in a mixing room where stainless steel blending tanks are used to combine raw ingredients such as whole milk, cream, skim milk powder, sugar, corn syrup solids, and stabilizers like guar gum or carrageenan. These ingredients are stored in separate bulk storage silos or tanks at controlled temperatures and are pumped into the mix tank using automated volumetric dosing systems. The control panel interfaces allow operators to select a formula code that precisely dictates the ratios required for each batch. As the ingredients are added to the tank, high shear impellers begin to mix the contents, breaking down solid particles and dispersing fats evenly into the water phase. The temperature is kept in the range of 40 to 50 degrees Celsius to aid solubility and prevent premature thickening. Once mixed into a smooth liquid, the batch is sent through a plate heat exchanger where it is heated rapidly to pasteurization temperatures, usually around 82 to 85 degrees Celsius, and held for 25 to 30 seconds to eliminate any harmful bacteria and extend shelf life. This pasteurization step is monitored using digital sensors that track the flow rate, inlet and outlet temperatures, and holding times. Immediately after pasteurization, the base is cooled just as rapidly by the second half of the heat exchanger using chilled glycol solution or water, dropping the temperature of the mix to around 4 degrees Celsius. This chilled mix is directed into insulated aging tanks where it is gently agitated and held for a minimum of 4 hours. The aging process allows the milk fat to partially crystallize, which improves body and mouthfeel, while stabilizers fully hydrate and develop viscosity. The aging tanks are jacketed and equipped with temperature controllers to ensure the mix stays cold and consistent across the entire volume. From the aging tanks, the base mix is pumped through a filtration unit and into continuous freezers. These freezers are the heart of the transformation process, where liquid mix becomes soft, semi-solid ice cream through a combination of rapid cooling and mechanical aeration. Each freezer consists of a horizontal freezing barrel that's jacketed for refrigeration and fitted with a rotating dasher blade assembly that scrapes the frozen mix from the inside wall while simultaneously blending in air. This air is filtered and injected under pressure to create overrun, the volume of air in the ice cream, which typically ranges from 60 to 90% depending on the product line. The dasher speed and airflow rate are tightly controlled to produce a uniform texture with consistent aeration. As the mix freezes, small ice crystals begin to form, stabilized by the partially solidified fat structure. The blades continue to whip the mixture while keeping the internal temperature around 5 to 7 degrees Celsius, cold enough to form a spoonable texture without fully hardening. At this stage, inclusions like chocolate chips, cookie dough, brownies, caramel swirls, or fruit pieces are introduced. These mix-ins are added using ingredient feeders synchronized with the freezer output. The feeders are auger-based or belt-driven and feed precise quantities of inclusions into the flow stream so that distribution is even but gentle, ensuring that delicate ingredients are not crushed or smeared. As the frozen mix exits the freezer, it is immediately deposited into containers. Bluebell typically uses round paperboard cartons with plastic-coated interiors for ice cream, ranging from pints to half gallons. These cartons are automatically erected from flat stock, positioned on a conveyor belt, and filled via time pressure or piston-based filling heads. The heads are height adjustable and retract as the filling occurs to prevent air pockets or overflow. For varieties with variegates like fudge or fruit syrup, an additional stream is injected into the flow through a ribboning head, creating visible swirls as the carton fills from the bottom up. After filling, a lid is automatically pressed onto the container using pneumatic arms. The sealed containers pass through a rotary or linear check weigher that confirms the net weight is within spec. Underweight or overweight cartons are automatically rejected and sent to a separate path for inspection or rework. Accurate filling is essential not just for consumer expectation, but to ensure uniform freezing in the next step. The sealed containers are then conveyed into a hardening tunnel, which is essentially a long blast freezer where temperatures drop to 30 to 40 degrees Celsius. Inside, high-velocity fans circulate sub-zero air around the cartons, freezing the remaining liquid phase rapidly and reducing the core temperature of the ice cream to below 18 degrees Celsius. This fast hardening process is vital to preserving the fine ice crystal structure created during freezing. The air jets are angled and modulated to provide even exposure and prevent frost buildup or warping of the cartons. The hardened ice cream containers exit the tunnel and move into the packaging area, where they are inkjet printed with date codes, flavor identifiers, and batch numbers. These markings allow full traceability from raw ingredient to final sale. Cartons are grouped into multi-packs using collators and tray packers, then boxed by robotic case packers into corrugated shipping cases. Each case is sealed with tape or hot glue, scanned for correct labeling, and palletized using robotic arms. Pallets are stacked in specific configurations that maximize airflow for cold storage and are wrapped in stretch film to protect against moisture and dust. Finished pallets are transferred to a holding freezer, typically kept between 20 and 25 degrees Celsius, where product is stored until it's loaded into refrigerated trucks. These cold chain logistics are essential to prevent thawing and refreezing, which would cause ice crystal growth and negatively affect texture. Delivery schedules are timed to coordinate with storage capacity and retail demand, ensuring that the product reaches shelves still within the optimal quality window. Every point in the process is monitored through industrial control systems. Pressure sensors, flow meters, thermocouples, and programmable controllers gather real-time data on mix temperatures, freezer speeds, air injection rates, filling volumes, tunnel temperatures, and even ingredient feed rates. This data is reviewed both in real time and after production to analyze batch quality, identify issues, and implement continuous improvement measures. Any batch that deviates from target parameters can be traced back through digital batch logs and ingredient tracking systems, allowing for full quality control. In terms of sanitation, the Bluebell factory uses CIP, clean-in-place, systems on all tanks, lines, and freezers. After each production cycle, a sequence of hot water rinses, alkaline cleaners, acid washes, and final sanitizers is circulated through the system at high velocity. The cycle times, temperatures, and chemical concentrations are controlled automatically, and post-cleaning validations are performed using ATP swabs or microbiological plate tests to verify the absence of residue or bacterial growth. Mix-in feeders and surface equipment are cleaned manually between batches, especially when allergens or strong flavorants are involved. The result of all these carefully engineered steps is a product with uniform texture, balanced aeration, clean flavor release, and reliable scoopability straight from the freezer. Whether producing vanilla, cookies and cream, or limited edition seasonal flavors, the factory process remains consistent. Transform a raw dairy mix into a frozen dessert that maintains its integrity from the first pour to the final bite. Ben & Jerry's ice cream begins its journey inside large stainless steel mixing vats where fresh cream, condensed skim milk, and liquid sugars are combined in tightly controlled quantities based on batch-specific recipes, with all ingredients pumped from chilled storage tanks through sanitary stainless steel lines that use flow meters and valve junction boxes to direct each liquid into the blending vessel in the correct sequence, ensuring homogeneity without introducing unwanted turbulence that might destabilize the emulsion forming at the early stages of mixture development. The mixing vats are equipped with high-torque agitators and slow-speed sweep arms that rotate along the inside surfaces of the tank walls, scraping the mixture and pulling ingredients from the periphery into the bulk flow, preventing solids like stabilizers or milk powders from clumping or settling during agitation. While shear heads built into the agitator columns create localized high-energy mixing zones that dissolve particles evenly and allow for a uniform dispersion of all dry and liquid components. Once all base ingredients are integrated, including emulsifiers that help bind the fat and water phases and stabilizers that give the frozen product its structural resilience and slow down melting during consumption, the liquid base is pumped through a plate heat exchanger that rapidly raises the temperature to approximately 82 to 85 degrees Celsius in order to pasteurize the product, which not only destroys pathogenic bacteria, but also activates certain proteins in the milk that contribute to a richer, denser mouthfeel when frozen. After this high-temperature short-time treatment, the base flows immediately into a second section of the heat exchanger, where it is chilled using a closed-loop glycol or ammonia refrigeration circuit that drops the temperature back down to around 4 degrees Celsius in a matter of seconds. And the pasteurized, chilled base is then directed into jacketed aging tanks, which are maintained at low temperatures and fitted with slow, continuous agitators to prevent the separation of fat from the aqueous phase and to allow the stabilizers and emulsifiers to fully hydrate over the course of at least 4 to 8 hours. This aging step is crucial in Ben & Jerry's production process because it prepares the mix to accept not only high levels of air during freezing, but also unusually large and dense inclusions such as brownies, cookie dough chunks, peanut butter swirls, and toffee pieces that would otherwise sink or damage the structure of a weaker base. The aged mix becomes a foundation that can support extreme texture variation without phase separation or flavor loss. Once the aging process is complete, the base is pumped into continuous freezers that serve as the mechanical heart of the frozen transformation. And here, the mix is cooled down to roughly 5 to 7 degrees Celsius while being whipped rapidly inside a horizontal freezing cylinder, where rotating stainless steel blades scrape frozen mix from the walls and simultaneously fold in filtered air through precision-controlled injection valves that regulate the overrun, which is kept deliberately low, around 20 to 30%, compared to typical supermarket ice cream, in order to preserve the ultra-dense, ultra-creamy signature texture that defines Ben & Jerry's. The low overrun means that each scoop contains more ice cream by weight and less air, which makes the freezing process even more critical because dense product holds and transfers thermal energy differently than aerated product. And the refrigeration system must respond in real time to flow rate changes, viscosity spikes due to mix-ins, and fluctuations in pump back pressure, all of which can affect the crystal size and final structure of the ice cream. At this point in the process, flavors and inclusions are introduced using multi-head ingredient feeders, which are synchronized with the flow of frozen base to meter out solid components like brownies, peanut butter cups, or cookie swirls at a controlled rate, using screw conveyors or belt-driven chutes to deliver exact portions into the stream without breaking or over-mixing the inclusions. The goal is to allow each piece to be suspended in the flow with minimal shearing or melting, preserving chunk integrity and creating the variety of texture that Ben & Jerry's is known for. For variegates like fudge ribbons or caramel swirls, the freezer's output is directed into a stream-splitting pipe system where the flow of base ice cream is divided and recombined with injected streams of liquid syrup using spiraled ribboning nozzles that introduce the syrup in twisting arcs, embedding them throughout the product without fully blending them in, and allowing distinct, bold streaks of flavor to appear visually and texturally when the final product is scooped or cut. The combined ice cream and mix-ins flow directly from the freezer head into automated filling stations, where pre-formed pint containers made of wax-lined paperboard or biodegradable composite are delivered via a conveyor, raised into position by a pneumatic lift, and filled from a piston dosing head that controls both the volume and height of the deposit to minimize air pockets while achieving consistent fill weights across thousands of pints per hour, And the filling process includes an overfill compensation stage where a small mound is left at the top to account for post-fill settling and shrinkage during hardening. Once filled, the pints move immediately to a lidding station where domed plastic lids are placed and pressed down using synchronized arms that index precisely with the conveyor's motion, ensuring a tight seal without deforming the container. And each lid is automatically printed with a batch code, timestamp, and flavor identifier using laser or thermal inkjet printers that connect to the plant's centralized batch tracking system, which records every data point from base formulation to final packaging for regulatory compliance and internal quality control. From here, the sealed pints enter a spiral hardening tunnel, which is a vertically stacked freezer that uses high-velocity, ultra-cold air blown at 30 to 40 degrees Celsius to extract heat quickly and reduce the core temperature of each pint to below 20 degrees Celsius within minutes. And this rapid hardening is necessary not just to finalize the freezing process, but also to lock in the structural suspension of inclusions and prevent large ice crystals from forming during storage. The airflow inside the hardening tunnel is controlled by a network of fans and directional baffles that ensure every container receives uniform exposure regardless of its position on the spiral belt. And exit temperature is verified using inline infrared thermometers or embedded probes that signal if any container is under-hardened and needs to be rerouted or rejected. After hardening, the pints are automatically collated into case packers that group them into cardboard boxes or cartons, often 6 or 12 per case, and these cartons are sealed with either tape or hot glue before being labeled with shipping codes and scanned by barcode readers that confirm destination, flavor mix, and inventory count before the cases are stacked by robotic palletizers that arrange cartons into pallet configurations optimized for freezer airflow and shipping stability. Each pallet is stretch-wrapped with cold-safe film, labeled with a master batch and product manifest, and transferred into deep storage freezers that maintain ambient temperatures between 25 and 30 degrees Celsius to prevent even microscopic temperature fluctuations that could cause texture degradation, especially for pints containing swirl-based variegates that are sensitive to heat migration and sugar inversion if stored improperly. Throughout the factory, process control systems monitor every mechanical and thermal parameter, from ingredient metering to packaging fill rate, using SCADA software that aggregates live data from flow meters, temperature probes, mixer speed controllers, and inclusion dispensers. And this information is used both for real-time error detection and long-term quality analysis that allows production managers to fine-tune the sequence of operations and ingredient preparation for future batches. Every component that touches the product is cleaned using CIP clean-in-place systems that route caustic and acidic cleaning solutions through closed-loop pipes, tanks, freezers, and depositors, followed by hot water rinses and sanitizer cycles that are validated through swab tests and chemical residue sensors. And lines are completely stripped and reassembled during allergen changeovers or seasonal flavor transitions to prevent cross-contamination. Ben & Jerry's factory process is designed not just to produce a high-quality ice cream, but to do so with a level of texture complexity and inclusion density that requires more robust mechanics than standard ice cream production. From the strength of pumps used to move mix with dense brownie pieces, to the tolerance of nozzles that must deposit syrup without clogging or over-mixing. Each component is selected and calibrated to handle the brand's commitment to chunky, swirly, intensely flavored ice cream with integrity and repeatability.